All right, guys, Rajiv here from Math Vibes, and this is the second installment of Physics Live. So, Zaria, could you recall what we did yesterday? Physics, Fazella, physics, right? Zaria, can you recall what we did yesterday in physics?
We did mechanics and we looked at center of gravity questions, pressure questions, calculating moments.
Right, right. And we would look at Hooke's law as well, right?
And the SI units and stuff.
Okay, great. So before I move on, I want to finish this Hooke's law question, right? And I want to make sure you completely understand what was going on here because I know when I was doing this, you was kind of falling asleep, yeah?
Yes, sir.
All right. So in this question, they gave us some measurements for load and length, right? And they asked us to plot a graph of length versus load. So whichever one comes first is the y-axis, and whichever one comes second is the x-axis. So Zaria, for this graph, we plotted length versus load. Understand that?
Mm-hmm.
And this was the scale we came up with. Awesome. Now the next question was to determine the gradient of the graph. Now to find gradient, how much points do I need?
2 points.
I need 2 points, right? And can I take points that are given to me from the measurements?
No.
No, I can't. I need to do a best fit, right? And from there, from that best fit line, I will take my points. Do you understand why I took these nice points?
Because they're not like in between any of these small blocks. They're easier to read off.
Exactly, exactly. I call this one the first point and I call this one the second point. And using the gradient formula, y2 minus y1 over x2 minus x1, I was able to find my gradient. Now, if it's y2 minus y1, that is change in y. What will we measuring on the y-axis,
The length.
right? And I measure length in meters, correct?
Mm-hmm.
And on the x-axis, I was measuring load. And load is a force, which is measured in newtons. So are you okay with the units?
Yeah.
Right? Great. All right, part C now. What information about the spring does the gradient of the graph provide? Now, let me just give you a quick recap on this again, right? Because I feel like you didn't fully understand it last night. So do you remember that Hooke's law says that the extension of a spring is directly proportional to the force applied, granted that the elastic limit is not surpassed? Let me know if you understand that.
Yes, I understand.
Right. Everybody else in the Zoom, do you understand that if you pull a spring, right? The greater the force you apply, the greater the spring would extend? Yes or no? Let me know if you
Yes,
understand.
sir.
Right.
Yes, sir.
But it reaches a point where if you pull it, the spring will not be able to go back to its original position. And at that point, you would say that the elastic limit was surpassed. For those of you that don't know what elastic means is a property of an object to go back to its original position after being stretched. So if you pull a spring too much, you will surpass its elastic limit and it will no longer be able to go back to its original position. So are we okay with Hooke's law? Are we okay with Hooke's law?
Yes, sir.
Right. Now, Zaria, your relationship for Hooke's law is the force is equal. Actually, I'm going to throw in some maths here, right? Zaria, you doing maths in January or not? Tell me.
No. May June.
Okay. Did you do proportionality in regular maths? Yes or no?
Yeah.
All right. So in Hooke's law, I'm saying that the force is directly proportional to the extension, right? So in the next line, I would say that F is equal to what?
To E.
Not just E.
K.
Exactly.
K.
It's equal to KE, where K is my constant of
I'm not sure.
proportionality, right? That's what K
Okay.
is. Right. Now, I want you to realize that this kind of looks like the form y is equal mx. And furthermore, right? Furthermore, granted that the elastic limit is not surpassed. What kind of line is this? Isn't that a straight line?
Mm-hmm.
And all straight lines follow what equation?
Y equals mx plus c.
Exactly. Now you notice that this line starts at 0, 0. So that's why you're not seeing anything added on over here because it's just plus 0. But the main thing I want you to learn from this is that f is equal to ke is a line. That's a line, right? And it'll be uniform y is equal to mx plus c. So if I plot a graph of f versus e, what am I supposed to get from my gradient?
Zero.
Nah.
Wait.
So I want you to compare this and this. So y would be f, x would be e, what would m be?
Okay.
Exactly.
Gradient type.
Exactly. So if I plot a graph of f versus e, my gradient will give me
A.
exactly. If I plot a graph of f versus b, f versus e, my gradients will give me k. And in case you all don't know, in Hooke's law, K actually corresponds to the stiffness of the spring. In case you didn't know, K is the stiffness of the spring. And does that, let's see if that makes sense, Zaria. Zaria, if you apply a force to the spring in your push point pen, right? Let's just say you apply a certain force to that, and you apply the same force to the spring in the suspension of your car. Which one is going to extend more? The spring in the pen or the spring in the car? You tell me.
Is spring in the pen?
Exactly. So there's something we need to relate the force and the extension, and that is key, right? Depending on what the value for K is, it would mean that we need to apply more force, right? Or less force, right? So K just corresponds to the stiffness of the spring. How stiff is the spring? All right, so you understand this, right? If I plot a graph, if I were to do a graph of F versus E, my gradient is?
E.
Exactly. My gradient is K, right? My gradient is K, right? Yeah, and that's it. Oh, wait a give me a second, guys. Yeah, guys, back to what I was talking about. So, Zaria, if I plot a graph of force versus extension in the linear region of the graph, granted I don't surpass the elastic limit, my gradient will give me what?
It'll be equal to K.
Exactly, right? Exactly. Right. Now, if you have a graph of, let me explain something, right? If you have a graph of force versus, say, length, your graph is going to look a little different, right? And let me explain why. So, Zaria, end extension will be the difference in length by applying a force. So, like maybe you might take the original measurement and you might then stretch it, and you'd measure the new measurement, and then you would subtract it to find how much it extended by. Yeah?
Yeah.
Okay. If you plot on a graph of force versus length, the spring would have an initial length.
Yeah.
Yes. So do you think a graph of F versus L would start at the origin, or it would start somewhere over here or over here? What do you think?
I think it would start somewhere else in the graph.
It would, right? So watch this. If you have a graph of force versus length, it's actually going to look out something like this. And if you're curious as to why, when you apply a force at 0, wouldn't the spring already have a length? Think about it. Right, so this is what the graph look like. Now the gradient is still going to give you k, right? The gradient is still going to give you k. So that's what's going to happen if you have a graph of force versus extension and force versus length. Now let's look and see what happens if you have the opposite scenario. So force versus extension and force versus length, M is equal to Q. So if I do the opposite now, so Zaria, let's just say I do the opposite, right? Instead of F versus E, let's just say I found E versus F. What do you think my gradients will give me?
See?
Say that again?
See?
Nah. If F versus E gave me K, then E versus F would actually give me 1 over K, which is the inverse, right? 1 over or K to the power minus 1, right? I think about it, like it makes sense. A graph of F versus E will give you a K. So if you switch the order, then you'll get the inverse of the spring constant by finding the gradient. Does that make sense?
Yeah.
All right. And it's a similar concept if you had, let's just say instead of E, you had L, right? So Zaria, if you have L, and the spring would have an initial length before you extend it?
Yes, sir.
Yeah, it would. So it would look a little something like that, right? But if you were to find the gradient in the linear region, again, your gradient would be 1 over K, which is equal to K inverse. So if you have a graph of E versus F, right, or L versus F, the gradient is going to give you the inverse of the spring constant. So gradient will give you K to the power minus 1 or 1 over K. Guys, let me know if you'll understand this so far.
Yes, sir.
All right. Is there anybody that didn't understand this at all? Okay. So Zaria, you understand this, right? Let me know.
Yes, I understand.
Awesome. So Zaria, in this graph, we were actually plotting length versus load. Length versus load. So what will our gradient be? Length versus load. Would it be K or would it be K inverse? So Zaria,
K inverse?
yes, it would be K inverse, right? So the gradient gives us the inverse of the spring constant. Let me know if you understand part E, part B, part C.
Yes, I understand. All the parts.
Great. Use the graph to find the original length of the spring. So Zaria, imagine you have a spring, right? Imagine you have a spring. If you apply a force of 0 newtons, would the spring extend or would the spring just be at rest?
It would be at rest.
Exactly. So if I want to figure out the original length of the spring, I would need to go on my graph and see where the force is what?
0.
Exactly. Where is my force 0 newtons? So if we are on the y-axis, what is the x value? Tell me, if you are on the y-axis, what is the x
0.
value? Exactly. So can we both agree that this is what we're looking for? Like we are essentially looking for the y-intercept. Let me know if you understand that. Now, I'm gonna cheat a little bit here, right? I'm gonna cheat a little bit here. Give me a second. Watch this, right? Um, let me see how that looking. Okay, does that still look like a good best fit? Wait, so let me just adjust it slightly. Give me a second. I adjust it slightly. I'm trying to do some MacGyver type stuff over here so that the wine step would be easy to read. But I think we can read off this one over here. Shouldn't be that hard. Sorry, I think you'd be able to read this off.
I think so. I
Uh,
can't really see.
I think we could, right? But here what? This is a little Hackney exam. If you know that the y-intercept might mean something, when you're doing the best fit, right? A way to like kind of pull a smart move. Make sure it passing through like a dead like a block now. And it's not in the middle, right? You could there's a little hacker given you. Right? I didn't think about that. So this looks like it's in the middle, right? Can we see that?
Mhm.
All right. Now for the scale that we came up with yesterday, it was such that every small block is 0.005 number.
Yes, sir.
So what would half a 0.005 be?
0.0 2.5 25.
That looking like it ends.
Mm-hmm.
All right, good. So let's apply that over here. So, and one big block would have be 0.025. Okay. So this would have been 0.025. So this point over here would have been 0.225, right? And if we go up by one more small block, wouldn't that be an increment of 0.005,
Yes, sir.
right? So we're going up by two 0.005s. So if that's the case, wouldn't that be, so it's 0.005, so that would be 0.010. I wonder if you understand that. If you're going up by two small blocks, that would be
Yes,
zero.
I understand.
All right. And this is in the half mark between the small block. So this would have to be 0.0025. I wonder if you understand that.
Yes, sir.
So I want to add up everything, right? And tell me, what is 0.025 plus 0.010 plus 0.0025? So we add up all of that for me. Let me add it up as well. Okay. Let me add that up, right? If my Casio calculator would come on, okay, it just came on. 0.025, right? We went up two small blocks, so that was 0.010, right? And then I went up half of a small block, so that would have been 0.0025. So 0.0375. Let me know if you're getting that.
Yes, I had the same.
Right? So this is 0.0375. Okay. People in the Zoom, are any of you all confused by this? If you are, just tell me. I'll go back to scale on how I got that.
That's I good, sir.
Okay. So 0 point, right? Give me a second, right? Give me a moment. So that would be 0.0375. But Zaria, we still have to do one more thing, right? Do you understand that from here to here, right? That is the 0.0375. But entry started at 0.20.
Yes, sir.
Gotta add the 0.20 to that. And when you do that, you should get 0.2375. So that's your final value over here. All right. So 0.2375. So just to go over this one more time. So guys, every small block is 0.005. So one big block will be 0.025, right? So this will be 0.025, right? And I would have to add that to the 0.20, but stay with me. So this is 0.025. I went up two small blocks, so that would have been 0.005 by 2, hence 0.010. So I would have to add this to this, right? And then I would have to add that to me moving up half of one small block. So after adding up all of that, I got 0.0375. So that would be what all of those small blocks add up to. But remember, we started at 0.20, so I have to add 0.20 to the 0.0375. So I got 0.2375. Zaria, some of you confused.
Let's understand everything so far.
Okay, good. So the original length would be 0.2375 meters. 0.2375 meters. Now in physics, if they do not specify, how much should you round off to?
2 decimal places, sir.
So that's my basis.
Right, so that would be 0.24 meters. Is everybody okay with that?
Yes, sir.
Okay, good. And just to elaborate, you find the original length when the force is 0. So for this graph, that would be a y-intercept because at this point over here, your force is 0. So if you don't apply a force to the spring, you'll get the original length. All right. Use the gradient to calculate the extension of the spring if a 0.7 kg mass hangs freely from one end of the spring. Hence, calculate the length of the spring with the mass attached. So Zaria, you there?
Yes, sir.
Right, so let's do this question together, right? First things first. What was my gradient?
0.24 meters.
0.0275. That was the exact gradient, right? 0.0275. So my gradient was 0.0275. And the units for that was meters per Newton. And that gradient represented K inverse, right? Let me know if you understand.
Yes, sir.
So question, if I wanted to actually find for K now, what would I have to do with the 0.0275? Do you know? You have an idea?
You have to get rid of the -1.
So yeah, you'd have to get rid of the -1. So what would you do, right? Is you would raise both sides to the power -1. Because when you raise a power to a power, what do you do with the powers?
They cancel.
That it'll multiply. So if I raise this to power -1, -1 by -1 is 1, and I'll raise this one to the power -1 as well. Basically, what I'm trying to say is, if you want to get your answer, you'll just need to flip this, right? If you have K inverse and you want to find for K, all you're going to do is you're going to flip this. So you can write it as 1 all over 0.0275, and that will give you a K. So all you have to do is just flip it. So plug it into the calculator and let me know what you're getting. One over 0.0275. Let me know what you're getting.
36.36.
That way, I guess, sir.
You got 36.36.
Yes, sir.
Right? And the units for that. So, Zaria, if it was meters per Newton and we flipped it, what do you think this is going to turn to?
Newton meters
right? Newton per meter.
minus, yeah.
Okay, great. So use the gradient to calculate the extension of the spring, all right? The extension of the spring if a 0.7 kg mass hangs freely from one end of the spring. Okay, not a problem, right? Tell me, Zaria, what's the main formula for Hooke's law? What's the main formula for Hooke's law? F is equal to what?
KE, sir.
Yes. So Zaria, that's the main formula, right? F is equal to KE. Well,
Okay, so
F is the applied force, K is the what?
the direct proportionality.
Right? K is the spring constant, or the constant of proportionality, and E is the extension, all right?
Yes, sir.
So they want us to figure out the extension, right? If I attach a 0.7 kg mass, right? First things first, let's look at the formula here. In the formula, you are seeing force, you are seeing spring constant, and you are seeing extension. According to the question, they actually want us to find the extension, yeah?
Yes, sir.
So I'm going to underline this. So for me to find the extension, I would need to know the force and the spring constant. Do I know what the spring constant is? Dr. Ma, do we know what the spring constant is?
So,
Oh,
we know the force.
we just found it out. Check it out. We just found it out. Remind me, our gradient here, right? It gave us the inverse of the spring constant, yeah?
Yes, sir.
So if I want to find the actual spring constant, I would just have to invert it. So I wrote 1 over 0.0275, and that gave me the spring constant K. So I have the spring constant. So I have K. The only thing I don't have is the force. So if I attach something that has a mass of 0.7 kg, would I be able to figure out the force?
Yes, sir.
Talk to me. How would I find the force of a 0.7 kg mass?
Like the formula.
Yes. What's the formula for force?
Force equals to ME,
Right.
mass times acceleration.
What is the mass in this question? What is the mass of the object?
The 0.7 kg mass.
Right. And what is the acceleration due to gravity here?
10.
10, right? What is 0.7 by 10?
7.
Right. So that'll be 7 newtons. Let me know if you understand that.
Yes, sir.
Okay, great. So question, don't I know what F is and don't I know what K is?
Yes, sir.
So from here, I just have to find for E. So if I wanted to find for E, I would have to divide both sides by K. And that will leave me with E is equal to F over K. For those of you guys that are confused, watch. If I divide both sides by K, the K is going to cancel off here and leave me with E. So E is just equal to F over K. All right, so Zaria, tell me what to plug in next.
The force, which is 7 newtons,
Right?
divided by 36.36.
So plug that into your calculator and let me know what you're getting.
That's 0.19.
We verify that. What are you getting?
0.19.
0.19? Okay. When I use the exact value, I'm getting 0.1925. And if you round that off to 2 decimal places, you're going to get 0.19.
Yes, I rounded it off.
Nice. And the extension, what do you think the extension is going to be in? Centimeters, meters,
Meters.
Yep, meters. Say with me so far, right?
Yes, sir.
Right, but we're not done. What did they ask us to calculate in the end?
The length of the spring with the mass attached.
Correct. Now, this is the extension. If you want to figure out the actual length of the spring, how would you figure that out? Try to figure that out.
The original length minus the
Nah, no minus. Minus. Wouldn't be minus. Think about it, right? If you want to figure out the total length of the spring, wouldn't the spring have a natural length by itself? Like if you don't have a force of, say, the spring just have a natural length.
Yeah.
And when you extend it, aren't you adding to that length?
Yes, sir.
So what do you think I should do if I want to figure out the length of the spring? The entire,
Well, you would have to add the extension plus the original.
right? So the original length is called LO, original length. And I'm going to add that to the extension. So that's going to be 0.24, which was my original length, right? Plus 0.19. And what are we going to get there?
0.43.
0.43.
Yeah. Meters.
Right. Nikolai, tell me if you understood everything I did so far.
Yes, sir.
All right. Now, guys, if I am correct, right? When I go on my graph and I take a read off at 7 newtons, what is my length supposed to be? Approximately what?
Repeat, sir.
All right. So Zaria and Nikolai and the rest of you guys. If I now go on my graph and I take a read off when my force is 7 newtons, right? What length am I supposed to get if I did my calculations correctly? Zaria, when we did the calculation, we found that by applying a 0.7 kg mass, my spring would have a length of what? What length did I end up with?
0.9 meters. 19 meters.
No, that was the extension. That wasn't the entire length of the spring.
That was the 0.43.
Yeah, Zaria, you see any 0.43?
Yes, sir.
So here what I'm saying, right? If you go on the graph and you take a read off of 7 newtons, you're supposed to see 0.43 or something around that, if we are correct. Let's verify that. All right, so 7 newtons would be over here. Does everybody agree? This would be 7 newtons.
Yes, sir.
And watch, this is 0.40. Watch that, guys. Wouldn't that be like 0.43?
Yes, sir.
Yes,
Yeah.
sir.
Zaria, look how everything makes sense, eh? Zaria, look how everything makes sense. That's 7 newtons, right? We actually take the read off. I want to blow all your mind. Physics is very cool. Physics real cool, you know. Tell you now, yeah?
Yes, sir. Cool. Once you know what you're doing.
Yeah, once you know what you're doing, otherwise it kind of infuriating, right? All right. So Zaria, the calculation we got over here was 0.43, yeah?
Yes, sir.
Right. Now, when we took the read off from our graph, let's see what happened. So this is 0.40. This is one big block over here. So this is 0.025. So far, this length over here, this would be 0. What? If I add 0.40 and 0.025, what would that be so far?
That would be 0.425.
Zaria, I need you to tell me if you're confused or if you understand what I'm doing.
So you add in the 0.40 and the 0.25?
Yes.
Oh, that'll be 0.425.
Do you understand why? Or not? Talk to me. Be honest. Be honest. I'm here to help you. If you're confused, just tell me. That's okay.
I don't really understand why you would add it.
All right. So the scale we came up with was every 4 blocks is 0.10, yeah? That
Yes,
was
sir.
came up with. So if I divide 0.10 by 4, then I would get that every big block is 0.025. Do it now?
Yes, sir.
So say for instance, you went one big block past 0.10. What would this now become? If I went up one big block past 0.10, what do you think this length would be?
It would be whatever the original thing that you started at plus the 0.025.
Exactly. And what do you get?
It'll be 0.110 plus 0.025. 0.125.
Okay. So it's the same concept. Look at this again, right? If this is 0.40, right? You would know.
Yes, sir.
Remember, we said every 4 blocks is 0.10. So 0.10, 0.20, 0.30, 0.40. You understand that, right? Yes or no?
Yes, sir.
And we went up by how much? It's one big block, and
Mm-hmm.
so if we went up by one big block, what would I have to add to 0.40?
0.025.
Understand it now?
Yeah.
Right. And then we went up one small block again. What is one small block equal to?
0.005.
Exactly. So I want you to add 0.425 to 0.005 and let me know what you're getting.
0.43.
Oh, are you seeing that? Zaria, are you seeing that? Oh, yeah. Tell me, oh, yeah.
Yes, sir.
What do you get?
0.43.
Oh, I tell you, it's bad enough, it's bad enough. Nicola, you seeing that?
Yes, sir. One question, sir. So we cannot just measure, just by saying this, right? We cannot just measure from the graph and just put on the answer there. So then
No,
that would be much marks.
naughty. No, you're going Santa Claus naughty list if you do that, right? You're not going to get any higher marks. You might get 1 mark, right? Let me explain. In the question, they said use the gradient. Use the what? The gradient, right? We found the gradient to be 0.0275. And if you have a graph of length versus load, the gradient will give you the inverse of the spring constant. So here what you thinking, Nikolai? Here what you thinking? You with me so far? Oh, by the way, before I continue, Zaria, I need you to tell me, how confused are you? Be completely honest with me. I want to know where you are, right?
I understand now that we cannot complete it.
So that again?
I understand now that we completed
Okay.
so far.
So, Nikolai, just to go over back this question to make sure you understand and everybody else pay attention, right? Nikolai, in the question, they said to use a gradient, right?
Yes, sir.
Right. Nikolai, this is a length versus load graph. So your gradient is the inverse of the spring constant, right?
Yes, sir.
Anytime you have a length versus load graph, or let me just say you have an extension versus force graph, the gradient gives you the inverse. So Nikolai, if you have K inverse and you want to find for K, you just need to flip this. So do you understand how I got K?
Yes, sir.
Now, Nikolai, why would they tell us to use the gradient? Well, what is the formula for Hooke's law? Is it not F is equal to KE?
Yes, sir.
It is. So you just found for K, right? So you know what K is, and they are telling you that we're going to attach a mass of 0.7 kg. If you attach a mass of 0.7 kg, wouldn't that mean you're attaching something with a downwards force of 7 newtons? With a weight of 7 newtons. Let me know.
Yes, sir.
Right. So sorry, are you following so far, right? We found for K, we found for force,
Yes, sir.
and we're going to just plug everything into this formula now. So F is equal to KE. You make E the subject, right? And E would be equal to 7 all over the spring constant, which was 36.36. We got our extension to be 0.19. Now, Zaria, I believe what was confusing you was, why are we going to add this? That was confusing, and
Yes, sir.
let me show you an example, right? Watch this. Let's just say we have a spring here, right? And let me just say that this spring has a length of, say, 2 centimeters, right? 2 centimeters, you would know?
Yes, sir.
If I now apply a mass to it, how would I actually find the extension for that? Talk to me.
You would have to add what it originally was plus what it is after you add the mass.
Not quite, but I get what you're talking about. Let me show you something, right? If the new length, so let me just say I don't know slotted mass to this, right? Let's just say the new length is 4 centimeters. How would I find the extension? It went from 2 centimeters to 4 centimeters. So how much did it
I
extend?
have to subtract what it is now from what it was before.
So the extension would be,
4 cm minus 2 cm.
right, it should be 2 centimeters. So do you understand how to find the extension?
Yes, sir.
So if I wanted to find back the original length, wouldn't I add the original length plus how much it extended by to get the entire thing?
Yes, sir.
Let me know if that makes sense. You feeling good with that one? We cooking with that one?
Mm-hmm.
Okay. So just to go it over one more time so there's absolutely no confusion. So I'm going to draw a spring here, right? I'm going to try to confuse you here. Hopefully I don't confuse you. Give me a length for this. Give me a length for this.
5 cm.
5 centimeters, I bet. 5 centimeters. Let's just say we have, and let's just say that both of these springs are attached to same platform, right? And let's just say I take this spring, hook it up to a slotted mass, right? And so I attach a slotted mass to this thing. Now, and you understand that if I apply a slotted mass, isn't this slotted mass going to have a weight that would pull it downwards?
Yes, sir.
Right. So if you pull a spring downwards, what's going to happen to the spring? Is it going to remain at the original length or is it going to extend?
Extend.
It's going to extend, right? So let's just say that it extended to 17 centimeters. How would I actually calculate the extension? So this is the original length, right? And this is the new length. This is the new length. So how would I actually find the extension?
That'll be the new length minus the original length.
Right. So the extension would be equal to the new length, which is 17, minus the original length, which is 5. And what is 17 minus 5?
12
Great.
cm.
So do you understand that the original aspect of the spring would have been 5? That's the original part, right?
Mm-hmm.
But can you see that we actually extended it by 12?
Yes, sir.
So again, if I knew what the extension was, and if I knew what the original length was, wouldn't I have to add them to get the total length?
Total length. Yes, sir.
Awesome. So does this make 100% sense for you now?
Yes, sir.
Are you feeling like this now? Oh, but if okay, say no more. Good. Right. And were you a bit blown away by the fact that the graph literally gave us the exact same thing?
Yeah.
Yeah, that was kind of cool, right? Because
Mm-hmm.
the graph gave us the exact same thing. That's crazy. That's crazy, right? But if you use the graph alone, you're not gonna get full marks, huh? You're not gonna get full marks. Just putting that out there.
Okay.
Right. So Zaria, how you feeling with regards to this question? Confusion or no confusion?
No confusion.
Okay, great. Great, we're cooking then. So Zaria, read part 3 for me.
Part 3. If the spring was stretched beyond its elastic limit, how would this affect the shape of the graph?
So let me show you something, right? Under normal circumstances, if you apply a force to a spring, wouldn't it extend proportionally?
Yes, sir.
But if you extend it a bit too much, wouldn't you break the spring?
No.
Yeah, you would.
Yeah.
And the whole function of a spring is that when
Yeah.
you would go back to its original position.
Mm-hmm.
If you pull a spring a bit too hard, will it go back to its original shape?
No.
No. You ever pull a spring a bit too hard before? Or no?
No.
No. Oh, that is why you probably are a little confused. Oh, I'm gonna look for a sacrificial spring. Do I have a sacrificial spring? Oh, be right back. I'm gonna find a sacrificial spring. Sacrificial spring, where are you? Yo, I'm back. We got the sacrificial spring. We got it. Guys, can we see the sacrificial spring? Wait a I'm gonna sacrifice the spring. I'm gonna sacrifice the spring. Right. So Zaria, can you see our spring over here? I mean if you see any
Yes,
spring.
sir.
All right. If I apply a force, right? Can you see that it goes back to its original position? See
Yes,
that?
sir.
And the more force I apply, what is happening to the length?
It's extending.
Now, what's gonna happen? Okay, if I apply too much force, what happens there?
It's not going back to the original state.
Exactly. So I broke the spring, right? I broke the spring. That's why I said sacrificial spring. Do you understand the statement?
Kill him.
Yeah, boy. And Zaria, do you understand that if I keep applying a force, it's just not gonna move, right? It's just gonna remain there because it's extended as much as it could extend. I mean, if you
Yes,
understand.
sir.
That makes sense for you? Let me know
Yes,
that.
sir.
All right. Put F in the chat to pay respects for the sacrificial spring. F, yeah. Oh boy. All right. So Zaria, does it make a lot more sense now?
Yes, sir.
Okay, cool. So this is what's gonna happen, right? So we just sacrificed a spring, right? RIP. Guys, I'm gonna take a picture of the spring, right? And I'm gonna put it in the notes. I'll be hilarious. Okay. When you see my screen, let me know, right? You guys see my screen?
Yes, sir.
Okay. So this is what's gonna happen, right? So if you have a graph of length versus force, the graph is going to look a little something like this. Now, guys, if two things are directly proportional to each other, it's going to be a straight line, right? So Zaria, you understand a straight line? It means that if one
Yes,
is
sir.
that one increases. But if I pull a bit too hard, and you saw what happened, right? When I pulled it a bit too hard, did it go back to its original shape?
No.
And after I kept applying force, did the length increase at all? Like I really
After
applying force here. Is the length increasing? No,
after you break the spring?
yeah,
No.
after I break the string.
No.
No. So what's going to happen, right, is the graph is going to it's going to have a plateau. And what that means is no matter how much force I apply, my length is going to remain constant. You understand?
Yes, sir.
So this is the point here where the elastic limit was exceeded. Calling the spring bob or bob, right? The graph. So when you just check the spelling for me, I think it's flat, like with an X. Just check it for me. Somebody check down Google for me fast. I think it's with an X. Right? I think it is. Somebody check that for me fast.
So I see nothing with X, honestly.
You know, see an X?
Nah, sir.
I'll just leave it plateau. Right? The graph will plateau. And you can say, i.e., if a force is, right, if more force is applied, the length is not going to change. All right, so Zaria, do you fully understand this now?
Yes, sir.
Great, great. Now, how would you identify the region where proportionality exists? So, Zaria, if we're talking about proportionality, right? Anytime you see the word proportionality, we're talking about a linear relationship, right? A linear relationship, which is a line. Linear relationship. So if they want us to identify the region where proportionality exists, right? It's gonna be the region where it's the region where the length varies proportionally to the load, right? Right? Comma, I dot E, the linear region. Right? So guys, let's try to understand that. How would you identify the region where proportionality exists? Now, proportionality means a linear relationship. So the region where the length what varies proportionally to the load, i.e. the linear region, right? So Zaria, can we both agree that over here is where the elastic limit was surpassed? Yeah?
Yes, sir.
You see this region over here? That region is a region where it is linear, right? And proportional. So how are you feeling about Hooke's law? Feeling okay about it?
Yes, sir.
Great. Nikolai, you feeling a lot better about it now, or like, let me know what's going on.
It's legal, you know, so.
Say that again?
It's legal.
Oh, it's legal. So I'm not feeling so well, otherwise I'll make him say it. All right. So Nikolai, wrap this up for me there. Read that for me. Classify each quantity shown in table 2 as a scalar or vector by inserting a tick in the appropriate column. So tell me, Nikolai, do you think load will be a scalar quantity or a vector quantity?
Would it be vector because it's based on magnitude and direction?
Right, because load is a force, right?
Yes, sir.
And if load is a force is a vector, right?
Yes, sir.
All right, extension. Extension is length. Is length a vector or a scalar quantity?
The scalar, sir.
All right. Talk to me, right? Tell me, Zaria, do you understand why I ticked vector for load, which is a force? And we understand that forces could be acted in any direction.
Yes, sir.
And you could have negative forces. Think of when we was doing which topic we did have negative forces, boy. Think of like upward and downward forces. The upward forces will be positive and the downward forces will be negative. Right? But you're okay with this, right?
Yes, sir.
Say no more. Say no more. Right. So that's it for Hooke's law. Let's do some energy questions now. Now, let me just give you all a crash course on energy, right? First things first, guys, when you're dealing with energy, you need to know what the conservation of energy says. The conservation of energy.
Energy cannot be created nor destroyed, but transfer from one place to another or one form. I think it's place so. I
One
don't
for,
know.
oh, you're good, don't worry. That's correct. So energy cannot be created nor destroyed, only converted from one form to another. Zaria, did you notice?
Yes, sir.
Okay, wood. Now, when we are dealing with energy, the main types of energy we'll be looking at CSEC physics is potential energy, and kinetic energy. Specifically, gravitational, right? Right? Does anybody know what gravitational potential energy is?
Isn't that the potential energies is the energy stored but in gravity?
Yes. So it is just simply the energy an object possesses by virtue of its height. And the formula for gravitational potential energy, right, which is G dot P dot E, is equal to what? Does anybody know?
Isn't that mgh, mass by gravity by height?
Perfect. Perfect. Zaria, did you know that? Yes or no?
I see it already, but I don't know it like off the top of my head.
All right, but after today, though, have it locked in, right? So
Okay.
gravitational potential energy is the energy an object possesses by virtue of its height. So if I take something and I move it higher up, it's going to possess more gravitational potential energy. And the way I like to think about it is, there's a higher chance of toppling over or falling down. Right. Yes, yes. So somebody asked, is this not the same formula used for potential energy? Yes, but a lot of teachers and a lot of people abbreviate it. It's really gravitational potential energy. Why? Look at the formula. It's mass by gravity by height. The only reason you have potential energy, right, is because of gravity. If you are in space, there's going to be no potential energy, right? Because space has zero gravity. So I hope that cleared it up. The full thing is called gravitational potential energy, right? And again, Nikolai, aren't you seeing gravity being used in the formula?
Yes, sir.
Yeah, gravitational potential energy, right? Okay. Zaria, do you know what kinetic energy is?
So I don't have like a definition for it.
So isn't that the energy the object has or something so? No, not no. Trying to remember it's from the top of my head now. It's energy. I know it has to do with energy, but that is like moving. That is when the object moving or
Yes.
something.
Yes, moving. So the kinetic energy is just the energy you would say is the energy, right? An object possesses by virtue of its motion. So if an object is moving, it is said to have kinetic energy, right? Right. So a moving object. All right. Sarah, did you know that or not?
No, sir.
All right. Well, now you know, right? Now you know. And the formula for kinetic energy, which is KE, is just what? Does anybody know?
So I forget this one.
All right, a half mv squared. Bringing any bells?
Yes, sir.
All right. And don't forget, guys, I believe I would have sent you all, like the document I sent you all, it had like a formula sheet with every single thing. The 17-hour live, that had a document containing all the formulas, right? Every single formula. Yeah. Watch a half mv squared gravitational potential energy mass by gravity by height, right? It's there. Everything is there, right? Okay. So, Zaria, are you okay with the law of conservation of energy,
Yes, sir.
right? Are you okay with gravitational potential energy?
Yes, sir.
And are you okay with kinetic energy?
Yeah.
What you will need to do, you will need to understand how to the conversion between gravitational potential energy and kinetic energy. You'll see how that will work out shortly, right? But take a screenshot of these things for me. And by the way, guys, what is energy measured in? Yes,
Joules.
energy is measured in joules. All right, so take a screenshot of that and we're going to move on.
Yes, sir.
Yes, Faith, this session is being recorded and it will be on my YouTube channel, Math Vibes. Right? Okay. So, do I have any other energy questions here loaded already? Never mind, fine. We'll deal with these. All right. So, Zaria, I want you to give 2A a read for me. 2A, a read for me. Give that a read.
2A, identify one alternative energy source utilized in or that is relevant to the Caribbean.
All right. Can you think of an alternative source of energy that is utilized in the Caribbean?
The windmill, like what do you call it?
Yeah. I know it's
So, isn't it wind turbines or wind terminals?
Mhm.
yeah, but it had a specific name for it. It wasn't just wind energy, it had a name for it. Let me find the exact name for it. What is the fancy name for wind energy? I know there's geothermal. Uh, okay, I never heard about this in my life. Aeolian energy, like Eolian. Okay, yeah, I never heard about that. Yeah, we'll just put wind energy, right? But let's identify the alternative energy sources, right? So there is solar energy, right? There is wind energy. There's geothermal energy. Are you all okay with these so far?
Yes, sir.
All right. Can you all think of any others?
I try to find, the water energy where they use the water, but I
Yes,
remember
hydroelectric energy.
yeah, I was trying to remember that name also.
Hydroelectric energy. Right. So you just have to put anyone over here, right? Identify one alternative energy source utilized in or that is relevant to the Caribbean. But you don't know why I'm going to put solar energy to real hot over here, sun real hot over here. Zaria, I sure you don't think of solar energy, right? And if you wasn't thinking about it, just leave the exam room, set up any sun for a little bit, come back in, and you'll be like, oh boy, wait. You know what I mean? Right? You okay with that, right?
Yes, sir.
Right. State two ways in which alternative energy sources, like the one mentioned in A part one, are important to the Caribbean.
Sir, we could have used nuclear energy as well, sir.
Yo, we are not Japan, bro. We are not Japan. We don't have the resources for that. Selma, are you seeing any of the Caribbean countries using nuclear energy?
So, really and truly, we don't know, sir. Like, they could be doing that and they're telling nothing about it.
That's true, but it's not it's not common, right? Stick with solar.
Yes, sir.
State two ways in which alternative energy sources, right, like the one mentioned in A part one, are important to the Caribbean. Right. So I see somebody on TikTok said energy diversification and energy security. Those are great answers. Right? What about the people in class here? Do you all have any suggestions?
Law we built, sir.
Say that again.
They say it mentioned in just now. Oh, so they want to know like reasons or something, sir?
It wants us to say, so like the one above, how is it important to the Caribbean? So let's
Oh,
let's
well,
let's try to understand this, right? In the Caribbean, how do we mainly generate our energy? By burning fossil fuels, I believe.
yes, sir. Fossil fuels.
Right? Now, is fossil fuels, um, is it a replenishable form of energy?
No, sir.
No. So it's not renewable, right? It's not renewable. So number one, so we could say energy security, and you could expand a little bit. In the Caribbean, specifically in Trinidad, actually you can leave out. In the Caribbean, fossil fuels is a main source of energy. However, it is not renewable. Right. And a good one would also be it's good for the environment. Let me explain something, right, Nikolai? Do you think burning fossil fuels is good for the environment?
No, sir.
No. So all of these ones mentioned over here, aren't these safe for the environment because you're actually utilizing the environment?
Well, yes, sir.
Yeah. So we could say better for the environment. Right? Better for the environment. Right? Solar energy is a form of green energy that does not directly harm the environment. So do you understand that by us using alternative energy sources, we are securing energy, right? So you're moving away from things like fossil fuels that are not renewable, and it's also better for the environment, right? All of these forms of energy mentioned here are green energy, and green energy doesn't really harm the environment much. The byproducts isn't bad. Let me know if you're okay with this so far.
What's that?
Yes, sir.
Are you all okay with this?
Yes, sir.
All right. Zaria, can you read part B for me?
State the law of conservation of energy.
Right. What is the conservation of energy? What does it say?
The law of conservation of energy states that the total energy before collision or explosion is the same as after the collision or explosion.
Nah, you are talking about the law of conservation of linear momentum.
Oh.
Yeah.
Isn't it the same definition I had said before, sir?
Exact same definition you just told me, right?
So that is the energy cannot be created nor destroyed, but transform. No, I forget it, sir.
All right. So energy cannot be created nor destroyed, only converted from one form to another. Right? So please remember that. Those are easy to marks again. Right? Let me know if you guys are okay with that.
Yes,
Yes,
sir.
sir.
Yes, sir.
Let's move on, right? Part C. A motor vehicle is traveling along a level road. What are the main energy changes taking place when the vehicle comes to rest after the brakes are applied? So I have a question, guys. They said something about level road. If it's level road, do you think there's any height? If it's a flat road. This was very important. If it's a level road, guys, if it's a level road,
Yes, sir.
is there any height?
No, sir.
No. So will there be any potential energy?
No, sir.
No, because gravitational potential energy relies on height. Right? Hear what I'm saying, right? Hear what I'm saying. Zaria, are you there?
So,
All right. Watch this, right, Zaria? Look at scenario 1 and compare it to scenario 2. In scenario 1, right, can we see that that is level road?
yes, sir.
In scenario 2, is that level road?
No,
No. So in scenario 1, will there be any potential energy?
no,
No, but in scenario 2, let's just say it's stop at the top of a hill. Will there be potential energy?
yeah,
Yeah. So in our final answer, there's not going to be any mention of potential energy, right? So they want us to say the main energy changes taking place when the vehicle comes to rest after the brakes are applied. So guys, if the car is coming to rest, what energy is getting converted? If something is moving, what type of energy does it possess? If it's moving,
Kinetic energy.
right? So my kinetic energy gets converted to what? When I mash the brakes,
Potential energy.
no. If you mash the brakes, right, two plates are going to slam against the, I don't really know, I don't really into cars, but just know it's going to slam against a metal disc, right? And
Sure.
if you're slamming something against a metal disc that is moving really fast, that is going to produce thermal energy, is it not? Through
Yes,
friction.
sir.
Through,
Friction, yeah.
so thermal energy, right? And after you mash the brakes, sometimes you will hear it, right? So that would
Yes,
be
sir.
with the sound energy.
And then you'd see some sparks if you're driving real fast.
Yeah. But these are the main three. So the kinetic energy gets converted to thermal energy because remember, the brake pads are going to slam against the metal disc, and that's going to produce a lot of thermal energy and sound energy. Are we okay with this?
Yes, sir.
That's the question, right? Thermal energy and heat energy is the same thing.
Yes, 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 yes. Right? A lot of students think it's not the same thing, but it's the exact same thing, right? So I'll make a note about that over here. Thermal and heat energy is the same thing. Awesome. Right, Zaria, you okay with this question?
yes, sir.
Right, I'll be honest, I hate these kind of questions. I much rather prefer the, like the calculation questions that actually test the physics. Like I don't like these kind of questions at all. I feel like it should be on a social studies exam, you know, asking me about alternative energy and thing. But yeah, it's not hard, it's just a lot more like social studies, right? Let's move on to some more fun questions. A lot more fun questions, actually. So, who wants to volunteer to do this question with me? Do I have any takers? Do I have any takers? I promise it's not hard. Talk to me.
All right, let me go.
Let me go. I give you a question. I'll read tomorrow.
An elevator rises a group of 12 persons to a vertical height of 10 meters in 5 seconds. If the average mass of the persons in the group is 55 kilograms, calculate the gravitational potential energy gained by the group. Use grams as 10 meters per second squared.
You just now say grams? Be careful, you know.
Oh, my bad. It's gravity.
Gravity, right? Gravity. So, first things first, right? An elevator raises how much people?
12.
12, right? Through a vertical height of, what's the height?
10 meters.
Now, they gave us that time for the first question is unnecessary, right? For the first question is unnecessary because
Yes,
they
sir.
find gravitational potential energy, right? Just sum fast. What's the formula for gravitational potential energy?
Gravity is equals to mass by the gravity by height.
Right. So we already have gravity, right? We already have the height. We need to figure out for the mass. So the next thing they're saying is if the average mass of the persons in the group is 55 kg, calculate the following. Now, I want Ola to be very honest with me. How much of you guys would have used the mass as 55 kg? Be honest with me. How much of you all would have used the mass as 55 kg? Zaria, would you have used the mass as 55 kg? Zaria?
Accent, you have to convert it.
Nah, converted is not
Yes, sir. And you would have to convert it.
conversion is not the right word to say because it's already in the SI units.
Okay.
We measure mass in kilograms, so there's no conversion to really do. But you see, the thing here that would tie up a lot of students is the part where they say the average mass of the persons in the group is 55 kg. So I have a question for you, all right? In the elevator, how much people does it have?
12.
Right. In the elevator, it has 12 people. You have 12 people. And on average, what is the mass of one of the persons?
55, sir.
55, right? So by the way, my approach with learning isn't like, use this formula, just put it in. I want to actually use all the brain and think, right? I want to come up with the concept and make sense of it. Guys, if they are saying the average mass of the persons in the group is 55 kg, does that tell us the total mass of everybody? Or does that just tell us the average of one person? What do you all think?
1%.
Exactly.
Mhm.
So guys, if I wanted to figure out the total mass of the 12 people, how would I do that?
You multiply.
12 multiplied by 55.
Yes, right? So you multiply this by 12. So the mass is actually 12 multiplied by 55. And what would you get?
660 kilograms, sir.
660 kg, right? And this will be the mass of all 12 persons. I want to let you be really honest with me. How much of you guys would have get caught on 55 instead of the 660? That's okay. The important thing is you're seeing your mistakes and you're seeing where you could go wrong. So when you're doing the exam, you're gonna know not to do that. Read between the lines. Right? It's telling us to use G as 10. So I'm gonna replace that with 10. And what is the height we're lifting the persons up to?
By
What's the height?
10.
10,
It
right?
is.
So we are going to end up with 6, 6, and that'll be 3 zeros, right?
Yeah.
3. And that's energy, right? So what do we measure energy in?
Joules.
Use.
Joules. Great. Is there anybody at all that did not understand this question? Talk to me.
So I think we're good.
Okay, good. Part 2. The power required to raise the group. Now, does anybody know the formula for power? So I'll give you a hint, right? I'll give you a hint. They gave us time, right? They gave us time. They gave us time. And we just now found for energy. So do any of you guys know a formula for power that contains energy and time?
Guys, work. Guys, work done over time.
Right. Energy is the same thing as work, right? So power is going to be equal to the energy, which is the work done all over the time, right? So guys, what was the energy I used?
Wow, that big number.
66,000, right?
66,000, sir.
And that energy was used over what period?
5 seconds.
Right. So you can think of power as the rate at which work is being done. That's what you can think of power as, right? So power is the rate at which work is being done. And Nikolai, let me know if you understand why why I'm saying that. Because watch, we're dividing energy by 5. So in other words, in every second that passes by, a certain amount of work is being done.
Yes, sir.
So what are you guys getting for that? Let me know.
We got 13,200.
You got 13,200.
Yes, sir.
And does anybody know what we measure power in?
What,
Pascal.
yeah? Or
Watts. We measure power in watts, right? Power is measured in watts. If you didn't know, now you know, right? And let me give a common example. And when you go shopping for a fast charger or a charger in general, and you will see like this 100 watts or 60 watts or 65 watts on it.
yes, sir. Or and in the bulbs as well too.
Exactly. All of that is telling you a measure of the power. So in other words, how much energy does it use per second? That is what it's telling you. Right? So Nikolai, do you understand that for every second that goes by, 13,200 watts of work is being done to lift the persons?
Yes, sir.
And if you multiply this by 5, wouldn't you get back the total amount of work that was done?
Yes, sir.
Yeah. So Zaria, sorry about that. Hey guys, let me know if you all understand this question. Let me know.
Yes, sir.
Yes, sir.
All right. So before we move on, let's just do a little recap, right? A little recap. Zaria, what is the formula for potential energy? Gravitational potential energy, to be specific. Tell me, Zaria, what is the formula for gravity? Tell me.
Okay, man, this spot.
Hey,
Sorry.
CX, I'm put you on the spot even worse. I'm telling you. I'm telling
So
you.
like memorize it. I was just following along.
All right. So I'm giving you some time to soak it in, right?
Oh,
Lock that in, right? Have that locked in. Gravitational potential energy and kinetic energy. Have that locked in, right? All right. So, Zaria, what is the formula for gravitational potential energy?
Mass multiplied by the gravity multiplied by the height.
Right. What is the formula for kinetic energy?
A half mv squared.
Right. A half mv squared. And energy is measured in?
Joules.
Right. And what's the formula for power?
That's that. I didn't memorize that one either.
All right. Yada, have it locked in. Have it locked in. Right? So,
Energy over time.
right. Right. Power is equal to energy over time. Right? And please remember that power is measured in watts, by the way, right? Power is measured in watts. And power is the rate at which work is done. Right. So Zaria, please remember these things. I beg you, for your own good. Remember these things. Gravitational potential energy is mass by gravity by height. Kinetic energy is a half mv squared. Power is equal to energy over time, as measured in watts. And power is the rate at which work is done. Right? And let me just give you all the definition for energy one time. Energy is the capacity to do work. Have you all ever seen this definition before for energy?
yes, sir.
Okay, great. So Zaria, have all of these things locked in, right? Let me know when you're ready to move on.
Yes, I took a screenshot.
Okay,
Sir,
talk to me.
there's a possibility I might get one in physics, but the thing is, I just forget some of them things.
Oh, I think you can get one. I taught somebody physics in 3 months and they got a 2. And they never even did an experiment in person before. I think
Oh,
I think you could definitely get one in CSEC physics for sure. For sure. right?
So it's all of this we doing here, sir. It's just easy stuff, sir.
That's good. I'm happy to hear that. Right? So give us a read for me.
The basketball of mass
Actually,
0 point.
I want Zaria to help now because you seem like you know what you're doing. Right, Zaria? I want to take you out of your comfort zone and make sure you actually understand these things. So Zaria, give the question a read for me.
A basketball of mass 0.44 kilograms was dropped vertically from rest at A, 12 meters from the ground as seen in Figure 2. Calculate the gravitational potential energy of the ball at the point of release A.
Okay, so first things first. Tell me, what is the formula for gravitational potential energy?
Mass times gravity times height.
Right, mass times gravity by height. What is the mass of my basketball?
0.44 kilograms.
Right? What is the gravity?
10.
10, right? Did they specify that? No, you see that lose a mark there, you know. You see that lose a... See that?
Mhm.
You have to use the one they specify. So it's going to be 9.8.
So, but wait, so how that make a difference, sir? If
Yeah,
you're the 10,
it would make a difference. 9.8 is actually 9.81, eh? It's like that's the exact one. But like,
yeah, I remember that, but I know for CSEC there is always estimated to 10.
but if they specify, like in maths, when they would say use pi is 22 or something, the same thing over here. If they tell you to use acceleration due to gravity as 9.8, you have to use 9.8, otherwise you're liable to lose marks. Right?
Okay, sir.
Height. Tell Mazaria, what's the height?
12 meters.
Right, so plug that into your calculator and let me know what you're getting.
Point 16.
You got 50 points.
16.
Let me check that myself.
So I get 51.74.
Yeah, that answer is so incorrect. So it's 0.44 by 9.8 by 12. Again, it has to be 9.8. I'm getting 51.74. So Zaria, check back that for me. Make sure you get
Yes,
anything.
I would make a mistake when I was entering the numbers.
Oh, okay. You're getting the correct answer, no?
Yeah.
All right, we're at 51.74. And we're finding for energy, and energy is measured in
Mhm.
joules. Great. You understood that question?
So
Yes,
to
sir.
be honest, the only thing that will get me with a lot of marks lost is those SI units, sir.
Yes, units.
Yes, sir. Like you see how this one is for joules, sometimes I wouldn't remember, I just put on the answer.
Now, okay, yeah. Well, that's what I do in practice, eh? Oh, yeah, always add up your units. Otherwise, okay. Um, 1 mark is for your formula, 1 mark is for the substitution, right? And 1 mark is for the final answer with the units. So, please put on your units, otherwise you will not get full marks.
Yes, sir.
Right. Sorry, I give this question a read for me.
Final velocity of the ball on reaching the ground 1.56 seconds later. Assume no loss of energy as the ball falls.
All right. So, this question a little mischievous, right?
So it's gonna say acceleration, which is V equals U A plus T or something, sir.
Yes, it is. But you could also say GPE is equal to KE, and you can find for V. You're going to get a slightly different answer though. And what would have confused a lot of students is they said, assume no loss of energy as the ball falls. But the safest thing to do here is to use V is equal to U plus AT, right?
Yes, sir.
Over here, right? Zaria, did you know about this formula? V is equal to U plus AT?
Yes, sir.
Yeah?
Pick us up.
Say that again?
That's like my biggest up. Like that whole series of formulas that look the same.
Oh, yeah, yeah. The Suvat equations. I hate them.
Mm-hmm.
I think I have the formulas over here. Supposed
To be honest, I remember
All
that
of it.
one only formula, so
I
I
must,
didn't remember the rest of them.
So I
I
don't like
must,
that it all just looks so similar, and then they have like similar things in each one.
I myself don't like it. I just derived them in the exam. I don't remember it. I just derived them.
So for tests, I just memorize that specifically, and as soon as I get the paper, I just jot it down one time.
That's what you had to do, you know? To be honest, that's what you had to do. Right. Right.
So you wouldn't mind resending this document later on, sir?
So I'll resend it. Right. So sorry, these are the five formulas, right? For linear motion. So sorry, yeah. They gave us the time here, right? They specified that the time would be 1.5 seconds later. Understand?
Okay.
And the acceleration will be the acceleration due to gravity, yeah?
Mm-hmm.
So let's just plug in everything. And what was the initial velocity? It was dropped from?
From rest. So 0.
Exactly. Right. So it's going to be V is equal to 0 plus acceleration due to gravity is 9.8 in this case, right? And the time is 1.56, right? So multiply that and let me know what you're getting. What is 9.8 by 1.56? Nine point eight.
So I got 15.29 meters per second.
Right, that's correct.
This is
Yes, sir.
Yeah, you're supposed to get 15.29 meters per second, right? Is everybody okay with this question?
yes, sir.
Sir.
All right. Let me just take this opportunity to just review these formulas quickly. So T is obviously time, and in physics, we measure time in seconds, right? V is final velocity, and we measure velocity in what? What are the units for velocity?
Meters per second or ms.
Right, meters per second, or ms minus 1, right?
Yes, sir.
What does U stand for?
Initial velocity.
Right. And Zaria, what do we measure initial velocity in?
So when it
Wait,
And
I want Zaria to answer this. Zaria, tell me.
initial velocity.
Mhm. What do we measure initial velocity in?
I'm not too sure about the units.
All right.
Not the same.
Let me try to understand this, right? So this is final velocity and this is initial velocity. The point is both of them are velocity. So if the units here is meters per second, what do you think the units here would be? It's same as velocity as well. So what would the units be?
Seconds per meter.
No, it'd be meters per second. Why?
Well,
Because both of them are measuring the same thing. What are both of them measuring?
velocity.
Exactly. And velocity is meters per second or ms minus 1. So hope you understand that. Right? S refers to the displacement, not speed. S is displacement. And displacement, you can think of displacement as length. So what do I measure length in? Somebody tell me.
meters, sir.
Yeah, meters. And yeah, I believe that's it. So take a screenshot of this.
Sure. If I get A, which is acceleration.
Oh, thank you. Yes. Acceleration. And this is typically acceleration due to gravity, right? Now I need to specify something. if it's vertical, if something is falling vertically, what is acceleration?
Minus.
Wait, Zaria, if you drop something vertically, what's going to cause it to accelerate downwards?
Gravity.
Exactly. So if you are talking about acceleration vertically, g is 10 meters per second. Right? And if you're talking about horizontally, typically it'd be 0. Because if it, how do it even make sense? If you're dropping something horizontally, right? G would be 0. Yeah, so take a screenshot of these guys. Take a screenshot. Right? As soon as you have a screenshot, let me know, right? Let me know.
Yes, I don't get already.
Right, Zaria, you have it?
Yes, sir.
Good. Part 3. We want to find the ball's momentum when it hits the ground. So could somebody tell me the formula for momentum?
That is initial momentum equals total.
Nah,
No, MV, sir, MV.
right.
Mass by velocity.
Zaria, do you remember doing momentum yesterday?
Yes, sir, but I don't remember the formula.
All right. So momentum is simply the mass times the velocity. So momentum is equal to mass times velocity. You okay with that?
Yeah.
Don't worry, Zaria. Before we end the session today, we're going to recap all the formulas you should know up to this point.
So, by the way, I write in May, June, not January.
You're right, in the physics exam in May, June?
Yeah,
Oh, I
I just thought you didn't know.
the way you was talking about the crash course, I thought you was writing this in January.
So, because I did like ask you about that a while back, like last year, for
Yeah.
May, June. So I just thought you like, you know, I did not see you. I didn't think at the time you would have thought I was talking about January.
Well, see, talking about January, boy. I see you writing in January.
No.
Oh, okay. Oh, phew. Yeah, I'll be having a physics crash course. Say that again. Somebody was saying something. Okay, I'm not too sure what that person said. But yeah, I'll have a crash course for maths, physics in June, right? May, June. Once I have time.
Okay.
Yeah. Heck, that'll most likely be in April before the exam. So tell me, guys, what was the mass of the basketball?
0.44.
Right. And what is its velocity? We just found that.
15.39, sir.
What is 0.44 by 15.29?
I got 6.72.
You got 6.72.
Yes, sir. Well, it'll be 6.73.
Let me just verify that. $6.73, yeah. Now, Zaria, let me just remind you how to come up with the appropriate SI units. So can we see that is mass over here? Can we see that? Mass? What do we measure mass in?
Kilograms.
Kilograms, right? What do we measure velocity in?
Meters per second.
Right, so my units is just kg meters per second. Easy?
Mm-hmm.
So you could write kg meters per second, or you could write kg ms minus 1. Right, that one is fine. So are we okay with this question, guys?
Yes, sir.
Okay, good. All right, let's move on. So for those of you guys that missed yesterday, we covered moments. We covered moments and linear momentum. We looked at collision questions. So you guys missed out on some good stuff.
Yes, sir. I must out on plenty.
Yeah, boy. Let's see if I could find was there an energy question in 2025? Okay, good. We can do this question. Then we'll move on. Right? So Zaria, again, I'm gonna put you on the spot, right? You are going to pass physics. You have to. You will. So we're gonna look at the questions in 2025, right? That's the questions we're gonna look at. Right. So Zaria, let me just erase these solutions. Yeah, so Zaria, give that a read for me.
Define the term gravitational potential energy.
Do you remember what the definition is?
No.
You take a screenshot?
Yeah, wait. I'll try to remember because I know the formula.
So it's the energy an object possesses
By virtue of its height.
right, by virtue of its height, right. And you can say that gravitational potential energy is just simply equal to mass times gravity by height, and its units are joules. Right? And it's with units, joules. Okay, you get that?
So,
It would. So I'd like you to read the question here in figure 2.
figure 2 shows Carioy, a basketball player in the National League in St. Vincent, going through his routine. B. As Carrier dribbles the ball with either his right or left hand, energy conservation takes place. List the energy changes which take place through the following stages as he dribbles the ball. Part 1, when the ball leaves his hand and strikes the ground.
All right, so I have a question, right? If the ball is floating in midair, right? What type of energy does it possess? So this would be the ground, right? And the ball will be some distance from the ground. So what type energy does the ball possess?
Gravitational potential energy.
Right. Right. So the gravitational potential energy, right? So the gravitational potential energy, right? It gets converted to what? So as it falls, right? It starts to gain motion. So the gravitational potential energy gets converted to what?
Kinetic energy.
Yes, because if I drop something, right, isn't the potential energy going to get converted to kinetic energy as it falls and gains motion? Does that make sense?
Yes, sir.
Right? Right. Nikolai, is there something about I didn't understand, or do you feel okay with that?
Sir, I feel okay with that, sir.
All right. Right. while the ball is in contact with the ground. So does anybody want to suggest an answer? So when the ball now hits the ground, right, the kinetic energy gets converted to what?
Potential energy again because it could go back up.
Yes, right, kinetic energy. But what type of potential energy? You have to be specific. So it would be elastic. Elastic potential energy, right? So let's list all of them one time. So Nikolai, what's going to happen, right? Can we all agree that the ball would bounce back upwards?
Yes, sir.
Now it's not bouncing upwards because of gravitational potential energy. It's bouncing upwards because of the elastic potential energy, right? Because the ball is elastic in nature. It's also going to produce sound energy. When it hits the ground, wouldn't it create sound energy?
Yes, sir.
Right? And when it hits the ground, there's going to be some friction. So there's also going to be what type of energy?
So I don't remember that, sir.
All right. If something hits the ground and it makes contact with the ground and there's friction, what type of energy is created? Anytime there's friction,
Heat.
right? Okay, let me know if you guys are okay with this. So when the ball hits the ground, right, the kinetic energy gets converted to elastic potential energy. Why am I saying that? I'm saying that because when the ball hits the ground, right, it's going to rebound. It's going to bounce upwards. And the reason for that is because of the elastic potential energy stored in the ball by virtue of the material used, right? And sound is also going to be produced, and heat energy is also going to be produced. Are we okay with this question?
Yes, sir.
Yes, sir.
All right. Part 3. When the ball leaves the ground and rebounds to his hand. So, guys, first of all, why is the ball bouncing back to him? Because of what type of energy?
Elastic potential energy.
Exactly. So the elastic potential energy, right, that gets converted to what? When it hits the ground and it rebounds, it starts to move. So it gains what kind of energy?
Kinetic energy.
Right. And when it rebounds to his hand and he's now holding the ball, what type of energy does it now possess?
Potential energy.
Yes, but specifically gravitational potential energy. Okay, let me know, guys. Are you all okay with this? Zaria, talk to me.
So I didn't really know what to do at first, but I understand when you went through it.
Well, let me go through it quickly again, right? So if the man is holding the ball, right now it possesses gravitational potential energy because it's some distance away from the ground, yeah?
So
Right? So this is a height over here. Now, when it hits the ground, it's going to want to bounce back upwards. And why is that? Because of what type of energy?
elastic.
Yes, exactly, elastic potential energy, right? And when the ball is moving in the air, right, it will have kinetic energy. And when the ball reaches back in his hand, that would be what? Talk to me.
Potential.
Yep. See, look, you understand it. Nice. Right. So read part C for me.
In a test to determine if the basketball with a mass of 1.1 kilograms is properly inflated, the basketball is dropped from a height of 1.5 meters and rebounds to a height of 0.8 meters. Calculate the energy lost by the basketball.
So let me ask that question. I dropped the ball from a height of what?
1.1 1.5 meters.
Right? And it bounced back to a height of what?
0.8 meters.
So did it was it perfectly elastic?
No.
Yeah. So it lost some energy in the process, right?
Mhm.
So let me hear how you would go about this. It's a 6-mark question. How would you go about this? Do you have any suggestions?
To calculate that the energy loss,
Yeah, to calculate the energy lost. We're dealing with height and mass. What kind of energy you think was lost?
gravitational potential energy.
Yeah, right? We could figure out the energy lost by calculating the gravitational potential energy. So, number one, we know that the formula is equal to mass by gravity by height here,
Yes, sir.
right? So let's try to understand this, right? So, original gravitational potential energy. So the original gravitational potential energy would be the mass of the ball, which is 1.1 multiplied by the gravitational constant. Are they specifying which constant to use here? Okay, they are not specifying, so we're going to use 10. If they don't specify, use 10, right? Right, by 10. And tell me, what is the height it would usually, okay, what was the height it was dropped from?
1.5 meters.
Right, so what is the original gravitational potential energy?
That's 16.5.
You got 16.5,
Yes, sir.
right? 16.5 watts. Keep in mind, we're finding for energy, right? So what's the units for energy?
Joules.
Joules, right? Great. And now we need to figure out the 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 um the rebound gravitational potential energy. So that would be the same mass, right? But what height did it rebound to?
0.8 meters.
Right? So I'll put 1.1 by 10 by 0.8, and what would I get?
Point 8.
You got 0.8. Nah, someone else sus for that.
8.8.
1.8.8?
Mm.
Yeah, 8.8. So I have a question, right? If the original gravitational potential energy was 16.5, and when it rebounded, it was now 8.8 joules, how would I figure out the energy lost?
You would subtract the original from the rebound.
You mean you would
Subtract the rebound from the original.
yes. So that would be 16.5, right? Minus 8.8. Let me know what you would get.
7.7.
Where you getting?
7.7.
Right. Now there was another way to do this question, right? A more efficient way. Now, some of you all, if you're an advanced physics student, you would know that there's a slightly different formula for gravitational potential energy, right? You would know that gravitational potential energy could also be written as mass by gravity by delta H, which is a change in height, right? Change in height. So, look at what I was saying, right? Nikolai, there.
Yes, sir.
Is it possible for me to figure out the change in height?
Yes, sir.
Right? So my mass was 1.1, gravity was 10, and my change in height would have just been 1.5, right, minus 0.8. Plug that into the calculator and let me know what you're getting.
Yeah, get the same answer, sir. And that is what I do, sir.
Yeah. Big up. Right? So these are two different ways in which you could get the same answer. Zaria, which one would you use? Wait, did I lose the document?
That's probably the first one because I like to see my working. I come down in that order.
You feel like that'll be easier to figure out
Yeah, more understandable. But I understand the second method though.
because in the second method, we could also look at it as what was the change in height? So we would have lost a certain amount of height, so we could just use that to calculate how much energy we lost. So happy to hear that you understand both methods, right? Let's see how much marks this be given away in CSEC physics.
Yes,
Nikolai,
sir. Nice.
Yeah.
I tell you, CSEC physics real easy, I'm being real. I like it more than get one. Sure. Right?
So
Talk to me.
there was one question in my end-of-term test. So I'll find it back and send it for you. It's a question that gives me real difficulty.
What topic was it?
It was based on density, but there was a lot of information that you had to substitute and then find density for it.
What if that was this question? I wonder, boy. Was it this question? Calculate the volume of seawater displaced by the yacht as it floats.
I think so, you know, sir. Wait, scroll back up a little bit. Oh, no. Oh, yeah. Look at that. I need this, sir.
Yeah, this is a slightly tricky question. You had to understand that they said float. If something is floating, then the upthrust would have to be equal to the weight of the object. And if that is the case, then according to Archimedes' principle, then the upthrust would have to be equal to the amount of fluid displaced. Yeah.
Oh, okay, sir.
Screenshot that thing.
So Ariel, miss out thing yesterday, boy.
Yes, sir.
All right, let me just finish up this question. Right, part D suggests two possible ways in which the energy was lost by the ball. So, Zaria, do you know about air resistance by chance?
No, sir.
All right. Let me give you an example of something, right? Where would you run faster, in air or in the water?
Okay.
In air, right?
Mhm.
Okay, did you know that air is actually a fluid?
No.
Well, now you know, right? Air is actually a fluid. It behaves exactly like a fluid. Let me ask you a question, right? If you have like a room with an AC in it, and you open the door, and you could feel the cold air like flowing out. So you ever feel that before? Like the cold air, you could like feel it flowing over your feet or like your hands or whatever.
Yeah.
So in case you didn't know, and in case the rest of you guys didn't know, air is actually a fluid. So you see the same way how you would get slowed down if you try to run in the water, in the sea?
Yeah.
Yeah, well, it's the exact same concept over here, right? It's the exact same concept over here, where that, air isn't dense. Air is not dense, we know that, but it still has some resistance. It still has some resistance because air is still a fluid, right? I see somebody in TikTok said to use a car with your hand out as an example. And that's a good example, right? Zaria, if you're driving, right, and you put your hand out of the window, and you would feel the air gushing against your hand.
Yeah.
Yeah, that's air resistance. That's air resistance because and you feel like the air kind of pushing your hand backwards.
Mm-hmm.
Isn't that, think about that, right? Isn't the air pushing you backwards and preventing you from moving forward?
Yeah.
Yes, sir.
It's the same concept with the ball. Imagine the ball is falling but the air is opposing its motion. So let me know if you guys understand that. So number one, air resistance. Do you all understand air resistance?
Yes, sir.
Right? And it's the same situation like, okay, sorry, have you ever tried to punch seawater before or like water in general?
Yeah,
When you've tried to punch seawater, what has happened?
but it's kind of, well, it's feel hard, like it really go through,
It essentially resists.
kind of block you a little bit.
Say that again?
It'll kind of feel like it blocking.
So the proper word for that is that it resists your motion. Doesn't it feel like it's stopping you? Like if you
Yeah,
try to punch water, you're going to feel it resisting your change in motion. It has inertia. So what I'm saying is it's very similar with air, because the example that the person gave on TikTok, if your hand is outside of a car window, you'll feel like the air is pushing you back. So it feels as though the air is pushing you back and preventing you from moving forward. It's the same situation with the ball. So imagine that the ball is falling and the air is pushing it back a bit. So it's preventing it from falling. So it's preventing it from falling without losing some energy, because some energy will be lost in resisting the change in motion. So let me know if you understand that.
yes, sir.
You think so?
Yes, sir.
Could you also say like the surface area as well? Like if you hit the ball on the concrete, it could bounce back up. But like if you hit the ball on the sand, it would be less. It wouldn't go up as high as you want in the concrete.
Okay, so you're talking about dampening. Sand is kind of malleable, right? So it actually absorbs a good bit of the energy. That's what you're talking about.
So could that be an example, a possible way as well?
I don't think so, because I think in this example, they're dropping it on the same surface.
Oh, okay.
Yeah.
Thank you, sir.
So another example I would say is some energy, right, could be lost. Right? Some energy could be lost. Wait, let me not say lost. I'm moving into controversial territory there. Some energy can be converted, right? Some energy can be converted to sound and heat energy. So Nikolai, let's try to understand that, right? Let's try to understand that. So do you understand that energy can either be created nor destroyed, only converted from one form to the other? Do you understand that?
Yes, sir.
So if the total amount of energy was 16.5, when it falls and it hits the ground, isn't some of that energy going to be converted to heat energy or sound energy?
Yes, sir.
So when the ball rebounds, it's actually going to have slightly less energy than it initially had. So do you understand that?
Yes, sir.
Okay, great. So some energy can be converted to sound and heat energy. All right, Cesaria, how you feel about this? You understand it or not?
I understand it.
Okay, great. So let me just give you all a quick crash course on thermal physics, right?
So I remember doing a question like that like 2 days ago, sir.
Well, good. With the you want the greenhouse effect?
Yes, sir.
Okay. Right, so the main things I want you to be able to understand is I want you to be able to understand what specific heat capacity is. Do you know what specific heat capacity is, though? Zaria, do you know what capacity is?
Like a definition, but I know about it. I know it's topic and stuff.
All right, well, let me give you a formal definition. Specific heat capacity is the amount of energy. So the amount of heat energy required to change temperature of 1 kg of a substance, right, by 1 Kelvin or 1 degree Celsius. So this is the definition for specific heat capacity. It is the amount of heat energy required to change the temperature of 1 kg of a substance by 1 Kelvin or 1 degree Celsius. This is what specific heat capacity says. So in other words, how much heat energy would I need to add to a kilogram of something to increase the temperature by 1 Kelvin or 1 degree Celsius? Do you all understand what I'm saying there?
Yes, sir.
Yes, sir.
Right? And the units. Does anybody know the units for specific heat capacity?
Would not
Is it
be
joules per
joules.
kilogram per Kelvin or joules per kilogram per degree Celsius?
Yes. Hit the nail on the head. Right? So it's joules per kg Kelvin, right? Or you could say joules per kg Celsius. Or you could also write it as joules, right? Kg minus 1, K minus 1, right? I could write it as joules, kg minus 1, degrees Celsius minus 1. Let me know if you understand that.
Yes, sir.
Right? So again, specific heat capacity, and Zaria, I hope you're paying attention, eh? So Zaria, specific heat capacity is the amount of heat energy you have to supply to something to change the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius. Right? So Zaria, please just locked in. Right? And the specific heat capacity is represented by a common C. Right? Right? Common C. And the main formula associated with specific heat capacity is E, right, is equal to mc delta theta, right? Or sometimes you would see Q is equal to mc delta theta. Both of them mean the same thing, right? Sometimes you might see E is equal to mc delta T. Sometimes you might see Q is equal to mc delta T. All of these formulas mean the exact same thing. Which one are you all accustomed seeing? E is equal to mc delta theta, Q is equal to mc delta theta, E is equal to mc delta theta, or Q is equal to mc delta T.
The two E's, sir.
Yeah.
The most likely it is used those, sir.
Right. So you never saw the one with Q before?
No, sir, but
Nah.
physics teacher before used that, sir.
Okay, so E just how much energy I would need, right? And Q is the amount of heat energy. So they mean the same thing, exact same thing, right? So I'm going to use this one, right? And I want you to know that delta T, delta theta just means T2 minus T1, right? That's what delta theta means. All right, so make sure you'll have a screenshot of this. All right, let's look at heat capacity now. Now, heat capacity is denoted by a capital C this time, a capital C.
Excuse, sir. One question, sir.
Yeah?
I thought heat capacity was this equation, but specific heat capacity was the one where you had to substitute the C.
All right. What you're talking about is capital C is equal to MC. This is the formula for heat capacity. But this is the formula here for specific heat capacity. And if you want, you can make C the subject of the formula.
Yeah, that was what I was talking about, sir.
Yeah, you could, if they ask you for specific heat capacity, you'll make C the subject of the formula here. But if they give you heat capacity, right, you could just divide throughout by M to get the specific heat capacity as well. So there are two ways.
Oh, okay, sir. Thank you, sir.
No problem. Now, heat capacity, by the way, guys, anytime you see the word specific, just know we're dealing with 1 kilogram of a substance, right? If you do not see specific, then it's generalized. So heat capacity is just simply the amount of heat energy required to change the temperature right by 1 Kelvin or 1 degree Celsius. So heat capacity does not have kilogram in it. It does not have mass in it, right? And the units for heat capacity is just simply joules per Kelvin, right? Or joules per degree Celsius. Let me know if you guys are okay with that.
Yes, sir.
Right? Again, the capital C is heat capacity, right? And the common C is specific heat capacity. And M is just mass.
Yes, sir.
Okay, good. Gonna move on, all right? So the next thing I want to move on to is latent heat, right? Latent heat. Specific latent heat, right, of fusion, right, LF. Does anybody know about the specific latent heat of fusion? Yes or no?
Yes, sir.
Zaria, what about you? Did you do thermal physics in school as yet?
Yes, sir, we did.
You did or not?
Yeah, we did a while ago, though.
Okay. Well, let me just jog your memory, right? So again, you are seeing the word specific. If you see the word specific, you know that whatever you're going to do, it will have kilograms in it, right? If you see the word specific, it's going to come
Yes, sir.
right. So what does specific latent heat of fusion say? It says that it's the amount of heat. It's the amount of heat 1 kg
We did.
of
So, for 1 kg of wait, hold on, I know it.
is
The amount of energy that you would need to like to change the temperature.
no, not temperature. From solid.
Without the change in temperature.
Right. Right. Without emphasis on the without changing its temperature. Emphasis on that, eh? Emphasis on that. And the formula for this one would be E is equal to mLF. But LF is the latent heat of fusion, right? So LF is just the latent heat of fusion. Right, so Zaria, I want you to give this a read for me.
Specific latent heat of fusion is the amount of heat 1 kilogram of a substance is required to convert it from a solid to a liquid without changing its temperature.
Wait, do you like what that sentence on? Right. Can you give it a read now? It should make more sense.
Specific latent heat of fusion is the amount of heat required to convert 1 kilogram of a substance from a solid to a liquid without changing its temperature.
Right. Heavy emphasis on the without changing its temperature. And I'm going to try to explain it to you all in the most simplest manner. Guys, do you think the atomic structure for a liquid, gas, and solid will be the same? Yes or no?
No, sir.
Now, let me show you what we're talking about, right? And this is a very rudimentary example, but it's just so that you could it's just so that you all could gain some intuition. I don't really do chemistry, but this is just an intuitive way for you all to understand what's actually going on behind the scenes. So let's just say that this is liquid, right? Liquid, right? Liquid. I'm gonna call this gas. I'll call this liquid, and I'll call this solid. Now, if you guys had to guess, what would you say is the densest form of matter? A gas, liquid, or a solid?
Solid.
I was
Solid.
as well.
Solid.
Now, let's understand why that is. Now, in a gas, do you think the atoms are held very strongly together?
No, sir.
No, sir.
No, they could actually roam about very freely. For a liquid, do you think the atomic bonds are stronger than a gas or weaker than a gas?
Strong, yes, sir.
No, sir.
Right, stronger, but it's still mobile, right? It can still move about. It can take the shape of whatever you put it in. Do we understand that?
Yes, sir.
Mm. And with a solid now, the atoms have to hold a fixed structure, right? They can't really move about at all. Unless we're talking about metals, right? Metals have free electrons or mobile electrons, which allow them to be good conductors. But if we are talking about just gas, liquid, and solid, a gas has very freely, the atoms aren't really strongly tethered to each other. Liquids, they have a stronger force of attraction, but it's still very weak. And they could actually take whatever form you put them in. Solid, on the other hand, is very rigid. So let me just draw how the atoms would look like for this solid over here, right? Again, it's very rigid. So check this out, guys. Guys, can we see that the atoms for a solid is very closely packed?
Yes, sir.
Yeah, guys, a solid, if you put a, guys, will a solid take the shape of whatever you put it in?
No, sir.
No, Zaria, look at the atomic structure of the gas, liquid, and the solid. The gas, it doesn't really have a very strong connection, right? The liquids has a stronger connection, but the solids has the strongest connection. Can you see that?
Yes, sir.
Right?
Yes, sir.
Interatomic bonds. So the solid would have the greatest atomic bonds, and the gas would have the weakest. Now, what I'm saying is, when you are going from a gas to a liquid or a liquid to a solid, there is a point where the structure needs to be rearranged. Now, when the structure is being rearranged, there isn't a change in temperature. The energy is actually being used to change structure and make the bonds. So, do you understand what I'm saying?
Yes, sir.
So, sorry, here we're saying again, right? Do you understand that the structure for a liquid and a solid is completely different? Yeah?
Yes, sir.
So, if I want to go from, say, a solid to a liquid, I would need to weaken these bonds before I get it into a liquid. So that period where the bonds are being weakened, that is called latent heat of fusion. Right? And at that point in time, there's no change in temperature. However, the bonds are being weakened. So I hope you understand that. So, sorry, I'd like you to read specific latent heat of fusion one more time for me. Read that one more time.
Specific latent heat of fusion is the amount of heat required to convert 1 kilogram of a substance from a solid to a liquid without changing its temperature.
Right. And while that is happening, right, the main thing that's going on is that the atomic structure is being reshaped. New bonds are being formed, or well, in this case, it's being weakened such that it can turn into a liquid. All right. So the next one you need to look at is specific latent heat of vaporization. So if fusion was from solid to liquid, what do you think vaporization is?
Liquid to gas, sir.
Right. So specific latent heat of vaporization. And the symbol for that would be LV, right? LV. Right. I'm just going to borrow the sentence structure. The amount of heat required to convert a kilogram of a substance from liquid right? And the formula for this would be E is equal to MLV, right? Where LV would be the latent heat of vaporization. All right, guys. Sorry, I'd like you to read this for me.
Specific latent heat of vaporization is the amount of heat required to convert 1 kilogram of a substance from a liquid to a gas without changing its temperature.
So again, Zaria, what I'm trying to emphasize is the fact that, if you want to go from a liquid to a gas, there reaches a stage where the main thing you need to do is rearrange the molecules so that it can change the states. So at that point, there will be no change in temperature because all the energy will be focused on rearranging the molecules to go from a liquid to a gas. Because you can see that the structure for a liquid and a gas are different.
Yes, sir.
Sorry, can you see that for a gas, the atomic bonds are a lot more weaker?
Yes, sir.
Zaria, do you do chemistry by chance?
Yes, sir.
Yeah?
Yeah.
Yeah or no? Can I hear you?
Yeah.
Yeah? Okay. These things should be making some sense to you then.
Mm-hmm.
Does sense. Right. So I want you to take a screenshot of this. Right? Take a screenshot of that for me.
I guess I did.
Right? And the other thing you need to know when you're dealing with thermal physics, you need to know the kinetic theory of matter. Do you all know what the kinetic theory of matter is?
Yes, sir.
What is the kinetic theory of matter and what does it say? And I'm hearing you guys, right? So the kinetic theory of matter says that all matter is made up of, right, is made up of particles in constant random motion. Right? And by adding heat energy to a system, the particles gain kinetic energy right? And move further apart. Right, so Nicola, give that read from the kinetic theory of matter.
All matter is made up of particles in constant random motion. By adding heat energy to a system of particles, gain
Yeah, gain.
kinetic energy and move further apart.
Right, so what I'm saying is, if you heat up, let me explain something, right? Zaria, if I apply heat to a solid, it eventually turns to a what?
Liquid.
Right, and the reason for that is because when I apply heat, that heat energy gets converted to kinetic energy, and the particles inside the solid start to vibrate a lot more vigorously, and eventually they move further apart and the bonds are weakened, and that gives you a liquid. Understand?
Yes, sir.
That's what the kinetic theory of matter says. Right. So I think we can do some past paper questions now. Right? Before we do anything, let me just do a recap, right? All right, so guys, if there is a change in temperature, so if there's a change in temperature, I want you to use this formula here. If you see that there's a change in temperature, you use E is equal to mc delta theta, right? And don't forget, delta theta is just T2 minus T1. If there's a change in temperature, right? Okay, if there is a change in state, what formulas would you use if there's a change in state?
Louis?
E equals MLF, or the E equals MLV.
Right, Cesaria. Anytime you see a change in temperature, you are strictly going to use E is equal to mc delta theta. If there is a change in state, however, you use E is equal to MLF or E is equal to MLV. Can you remind me what LF stood for? Tell me that.
Fusion.
The latent heat of fusion, right? And that would be the energy required to convert what? Solid, sir?
A solid to liquid.
Right. And if we're talking about latent heat of vaporization, we're going from a liquid to what?
A gas.
All right, liquid to gas. Great, so let's do some questions. Right. Okay, so somebody other than Nikolai and Zaria, have anybody else? I can't really see who in the meeting, but somebody volunteer. Give it a shot. Do we have any volunteers other than Nikolai and Zaria? Okay, I guess not.
Feel like everybody's sleeping?
I feel so. I feel like everybody's sleeping. Right? I don't know what's going on there, you know. All right, but yeah, Nikolai, let me do this question, right? So give this a read for me.
Complete table 3 by inserting the correct symbol and the SI unit, which relate to the quantity shown in column 1.
Right. So specific heat capacity. What are the SI units for specific heat capacity?
And there was joules per kilogram per Kelvin.
Yeah.
Or it could be
So for this one, let me show you all the acceptable answers, right? You could have said, now, here what, right? They say SI unit, and the SI unit for temperature is Kelvin. So honestly, I would tell you to use the Kelvin one because the SI unit for temperature is not degrees Celsius. Understand?
Yes, sir.
So I would tell you to use joules per kg Kelvin. You can write that, or you could write joules kg minus 1 Kelvin minus 1. I mean, if you're okay with it.
Yes, sir.
Right? Zaria, tell me, what is the symbol for specific latent heat of vaporization?
So like the SI thingy.
Not a symbol.
Mm, the E equals to MLV.
Nah, that's the formula. I want to know the symbol for it.
I don't remember.
All right. So this is what I'm talking about. Let me check this out again. So I said that the specific latent heat of fusion would be a capital M, or say a capital L with a subscript F, right? And I said the specific latent heat of vaporization would be a capital L with a subscript of V. So Check it out, right? Specific latent heat of fusion is a capital F, common F. Specific latent heat of vaporization is a capital L, common V. Understand?
Yes, sir.
And if we're talking about latent heat of fusion, it's common L, common L. If we are talking about latent heat of vaporization, it's common L. So, what is the symbol I'm going to write for specific latent heat of vaporization?
Capital L, common V.
Yeah. Well, it's really a subscript V, right?
Okay.
Right. And what is the SI unit for specific latent heat of vaporization? Try to remember.
Mm. This is not the joules per kilograms.
Now, before you say anything, right? We are talking about latent heat of vaporization. Is there a change in temperature? For this, is there a change in temperature?
No, that's without changing temperature.
Exactly. So when you're looking at latent heat of vaporization, it's important to know that there's no change in temperature. So if there's no change in temperature, do you think temperature will be included in our units?
No.
No. So the units are just simply joules per kg. Right? So you could write that, or you could write joules kg minus 1. Right? Let me know if you're okay with that.
Yes, sir.
All right. Just to recap, right? What is the SI unit for specific heat capacity given by common C?
Wait, take a repeat.
What are the units for specific heat capacity?
Kilo, joules per kilojoules.
Yeah.
Joules per kilogram.
Joules per kilogram.
Or joules per degree Celsius.
Nah. What you just told me was for the specific latent heat of fusion or vaporization. Okay, what? I want you to read the definition for specific heat capacity for me. What is the definition?
That's the amount of energy you would need, the amount of energy that's required to change the temperature of 1 kilogram of a substance by 1 kilogram or 1 degree Celsius.
I mean 1 Kelvin.
Oh yeah, 1 Kelvin.
Right. So, listen to the definition. It's the amount of energy, so joules, required to change temperature of 1 kilogram, so hence kilogram, of a substance by 1 Kelvin or 1 degree Celsius. So it's going to be joules per kg, Kelvin, or what? Joules per what?
Or joules per kg per degree Celsius.
Yes. Right? And if you want, you could write it using the indice notation, but I have a feeling you're not going to write that. I have a feeling you might stick to the fraction and the slash.
Okay.
What would you stick to? The slash or the -1?
That is usually used the slash, so probably that.
Okay, good. And what are the units for capital LF? If I write capital LF, what does it stand for?
Latent heat of fusion.
Not just latent heat of fusion. If it's
Specifically.
right, specific. Now, if it contains specific in it, most likely I'm going to have mass in my units, right? I'm going to have mass in my units. So can you read the specific latent heat of fusion definition for me?
The amount of heat required to convert 1 kilogram of a substance from a solid to a liquid without changing the temperature.
Right. So they mentioned energy. So for sure, it's going to be joules, right? Right. And then they mentioned what?
without changing its temperature.
Right. If it's without changing temperature, then our units are not going to have temperature in it.
Mm-hmm.
So they said energy, and you're from changing from what to what?
Solids are liquid.
Right. How much? How much of the substance?
1 kilogram.
1 kilogram. So you need to say joules per kg.
Joules per kilogram.
Right. Understand? And what do you think that's for LV would be? And what would LV stand for? What would LV stand for?
Specific latent heat of vaporization.
Yes, you have to say specific, right? And what are the units for that?
Mm. Joules per kilogram.
Exactly, joules per kilogram. Right? You okay with this?
Yes, sir.
All right. Okay, now you had to tell me the correct answer. What is specific heat capacity? What are the units for specific heat capacity?
The specific heat capacity are joules per kilogram degrees Celsius
Or
or joules per kilogram per Kelvin.
it's just simply joules per kilogram Kelvin, not kilogram per Kelvin, right? Right? What is the units for specific latent heat of fusion?
That'll be joules per joules per kilogram.
Yep, joules per kilogram. What about latent heat of vaporization?
It'll be the same joules per kilogram.
Exactly. Right? Nice. Right. So I want you to define the term heat capacity of a substance for me.
That'll be the amount of energy required to change. So when you say that, you mean like the specific heat capacity, like it matters? It's like two different things, so
Yes, it's two different things. If you see the word specific in your definition, okay, if you see the word specific, right? If you specific, just know whatever the definition is, it will include mass in it.
okay, well,
If
it'll
it
be the amount of energy needed required to change the temperature of a substance.
right, so the amount of heat energy required to change the temperature by how much? By how much?
Uh, it's hard to give you a mass if it's not specific.
Say that again.
If I have to give a mass if it's not specific, heat capacity.
If it is not specific, you not forget about mass. If it don't have the word specific in it, your definition cannot contain mass, right? So what I wanted to hear was
By not changing its no.
wanted to hear the amount of heat energy required to change the temperature by 1 degree Celsius or 1 Kelvin
Okay.
of a substance, right? Right? The amount of heat energy required to change the temperature by 1 degree Celsius or 1 Kelvin for a substance. So Zaria is specifically for 1 degree Celsius or 1 Kelvin, specifically for 1 degree Celsius or 1 Kelvin. Specifically. I know I'm saying the word specifically, and it might be confusing you. Just know 1 degree Celsius or 1 Kelvin. And if you don't see the word specific, if you do not see the word specific, are you going to include mass?
No.
You're not going to include mass. Right? Read part 3 for me.
Write the equation that relates specific heat capacity with heat capacity.
So, what is that equation? And remind me, what is the symbol for specific heat capacity?
Joules per kilogram.
Now, you're telling me the SI units. The symbol will be common C.
Okay.
What is the symbol for heat capacity?
The symbol for heat capacity is capital C.
Yes. What formula do you know has common C and capital C in it?
Capital C equals to M and then common C.
Exactly. Guys, are we okay with that?
Yes, sir.
Cool. Right, Cesaria, you ready to attack a kind of tricky question?
No.
No? I like the honesty. It's all tired. A little tired.
Yeah.
All right. So here
Sir,
what?
please.
Yeah, let me hear. So get the question I read from her.
Alright. A busy housewife left 25 grams of ice in an open insulated container while she was answering her cell phone. When she returned, the ice at 0 degrees Celsius was converted to water at 3 Celsius. 1. Calculate the energy needed for the ice to totally melt and to reach its present temperature. Assume no heat losses.
All right. So first things first, they give us the mass of the ice, right? But there's a problem there. They give us it in what?
Grams.
So how are we going to convert that to kilograms?
But, divided by 1,000.
Right. What is 25 divided by 1,000?
It will be it, 0.025. Yeah.
Right, 0.025 kg, right?
Yeah.
So she left 0.025 kg of ice in an open insulated container while she was answering her cell phone. So let me ask you a question, right? Logically speaking, if you leave ice exposed to the atmosphere, isn't it going to melt?
Yes, sir.
And over time, when it melts, and it's going to adopt the temperature of the atmosphere,
Yes, sir.
right? So let's understand what's going to happen. It's going to melt first, and at the immediate point at which it melts, what is the temperature of the water going to be when it melts?
When it melts, it's gonna be 3 degrees Celsius.
Now, let me ask that question. If you hold in a block of ice in your hand, right? When it melts, is it going to be 37 degrees Celsius or is it going to be cold?
Oh, it'll be cool. It'll be cool.
So, long story short, the immediate point at which ice melts, it's 0 degrees Celsius. Remember what has to happen? Let me show you what has to happen, right? Before you could actually heat up that liquid, what has to happen is that the bonds in the solid need to break and it would need to convert to a liquid. So when that is happening, there is no change in temperature. So in other words, latent heat of fusion. And if you're confused again, think about it. If you have a block of ice in your hand, when the ice melts, when you feel the temperature of the molten ice, is it cold or hot?
It's gonna be cool.
It's gonna be cold, right? And eventually, when the entire block of ice melts, and only then it will start to heat up.
Yeah.
Yeah. So it needs to be converted to a liquid first, and then that liquid will be able to be heated up. So,
I understand.
right? So let me just run you through the motions here. So initially, and it's gonna be ice.
Yep.
And the ice is gonna be at what temperature?
Is 0 degrees.
Right. Ice at 0 degrees Celsius, right?
Yep.
And this is a solid state, right?
Mm-hmm.
Okay. When the ice melts, so this is ice, it's gonna turn into water, right?
Yeah.
But like I just told you, the immediate point in which it melts, what is the temperature of the water going to be? Is it going to be 3 Celsius magically, or is it going to be cold still?
It will be cool. Then it will go to 3 Celsius.
Exactly. So it's gonna go from 0 degrees Celsius solid to 0 degrees Celsius water. Do you understand what I'm saying?
Yes, sir.
And this process is actually latent heat of fusion, right? Because what's happening is that the atoms in the ice, right, is going to be the interatomic bonds needs to be weakened and converted to a liquid structure. And When that is happening, there's no change in temperature. There's just a change in interatomic bonds.
All right, sir.
Imagine it like this. You have a Lego, right? The Lego is shaped like an ice block, right? But before you can turn it into water, you need to take the Lego blocks and disassemble them and put it in the shape of the water. That's what's happening. And that would take some energy.
Yes, sir, I understand.
Would. And when it's water, when the entire ice block turns to water, and it can now be heated up.
Yep.
Right? So this water over here, right, is now gonna, after some time when you leave it, it's gonna turn to what temperature?
3 Celsius.
Right. Okay. We have energy being supplied there and energy being supplied there. If we want to figure out the energy over here, right? Will I use E is equal to MC delta theta, or will I use one of the latent fusion formulas?
Latent fusion.
Exactly, I have to use latent fusion because are you seeing a change in temperature?
No, sir.
No. Right, so we're going to use E is equal to MLF, right?
Yep.
Right, and since there is a change in temperature here, and it's the same state, we are going to use E is equal to,
MLF.
now be careful,
Hmm?
not ML, E is equal to,
M is done. Sorry,
Yeah.
sir.
That's all right, it's fine. So let's actually get cracking now.
Yep.
So the first thing we're going to do is we're going to calculate how much energy it took to convert the ice to water, right? So E is equal to MLF. We found that the mass of ice was what? What's the mass of the ice?
0.025.
Right? 0.025. And they gave us the latent heat of fusion. And what was it?
340,000 kg minus 1.
Right. Right. So work that out and let me know what you're getting.
8,350 joules.
Right? 8,815.
No, 350.
Okay, 8,300. Wait. Something about that sound a little off. Let me just verify that. So 0.0.
I have 8,500.
They're getting 8,500.
Okay.
Plug that back into your calculator. 0.025 by 340,000. And let me know what you're getting.
Yes, sir. 8,500.
Right?
Sorry, sir.
And since it is energy we are finding for, what are the units for energy? What do we measure?
Joules.
Joules, right? Okay. Next up, we have E is equal to MC delta theta. Again, the mass of the ice cube, right? It was 0.025. Right, what is the specific heat capacity of water?
4,200 kg minus 1 Kelvin minus 1.
Right? And let me ask you that question, right? A lot of students ask me this. Do I need to convert this to Kelvin? Short answer is no, you don't. The reason why is because a change in degrees Celsius is the same thing as a change in Kelvin. Let me show you proof, right? Guys, how do I convert degrees Celsius to Kelvin? Remind me.
That is the degrees Celsius plus 273.
Right. So guys, if I had 0 degrees Celsius, right? What would 0 degrees Celsius be in Kelvin? What is 0 plus 273?
273 Kelvin.
Right. Okay, and if I have 3 degrees Celsius, right? To convert that to Kelvin, I'll say 3 plus 273. What is 3 plus 273?
276 Kelvin.
Okay, to the guy I was talking to just now, do you understand? These will be the readings in Kelvin, right?
Yes, sir.
Now, if I subtract those two from each other, what is 276 minus 273?
3.
And what is 3 minus 0? Right. So you see, the change in degrees Celsius is equivalent to the change in Kelvin. So you don't need to convert the temperature to Kelvin. I'm saying that. You don't need to convert it to Kelvin. It's just going to be 3 minus 0, right? Which is going to be 3. So plug that into your calculator and let me know what you're getting. Should get 315 joules.
Sure. Yes, sir.
Right? So altogether, how much energy would I have needed?
You would have needed 8,500 plus 315 equals to 866. I mean, 8815 joules.
Right. Okay, you understand that question?
Yes, sir.
All right. Okay, give this question a read for me.
If the melting and heating activity took place over 300 seconds, calculate the rate at which the ice or water was receiving heat.
All right, so talk to me, right? How long will it take?
300 seconds.
Right, so that's the time, right? The time is 300 seconds. And do we know the energy it took?
Yep.
What's the energy it took?
8,815 joules.
And in case you guys didn't know, the rate at which the ice receives heat, this is referred to as power. So they want us to figure out the power. Anytime you see the rate at which energy, anytime you see the rate at which work is being done, that is power. It's the same concept over here. The rate at which the ice is receiving heat, power. So we need to calculate power. Do you know the formula of power involving energy and time?
Yes, sir. Energy over time.
Right? Energy over time, yes. Right? What is the energy?
8,815 joules.
And how long did it take to supply that energy?
300 seconds.
So what was the rate at which the energy was supplied?
29.38 joules per second minus 1.
I see why you would say that, but the units of power, we typically write it as watts. But I understand why you would say that.
Okay.
Right? Because you said joules per second, because energy is joules and time is seconds. But power is measured in watts, right?
All right.
Yeah. Are you okay with that?
Yes, sir.
Okay, what? We are going to look at a particularly tricky question. Let me see how well you would let me see how well you're gonna handle that question.
All right.
Just so. All right, I want you to give this a read for me.
Yashoda prepared some lime juice on a hot day. She adds 80 grams of ice at a temperature of 0 degrees Celsius to 0.32 kilograms of lime juice. The temperature of the lime juice decreases from 29 degrees Celsius to 8 degrees Celsius, and all the ice melts. Latent heat of fusion of ice, 3.4 multiplied by 10 to the power 5 joules kg minus 1. Specific heat capacity of water, 4.2 multiplied by 10 to the power 3 joules kilograms minus 10 C minus 1. Calculate the energy required to melt 80 grams of ice and the energy gained by, so something is blocking last word,
All right.
by the melted ice.
All right, so you think you can handle this question?
Yes, sir.
All right, well, let's give it a try. So first things first, right? Yashoda prepares some lime juice on a hot day. How much ice does she add to the lime juice?
80 grams.
All right. So I'm going to draw a cup, right? And in the cup, it's going to have lime juice. So as it stands right now, this is the lime juice, right? By itself.
Mhm.
What is the mass of the lime juice by itself?
The mass will be 0.08 kg.
Nah.
Huh? Oh, the lime juice.
Yeah, the lime juice by itself.
Oh, sorry. 0.32 kg.
Right, 0.32 kg. Right? And what is the initial temperature of the lime juice?
It was 29 degrees Celsius.
Right. What did I add to that?
Ice.
Yep, I added ice. All right. Now, here it said, we actually do not know what the intermediate temperature is. We don't know. We don't know the temperature it was when you added the ice to the cup. The only thing we know is the final temperature. And I'll show you what I mean by that. So ends eventually the ice would melt.
Yep.
Right, the ice would melt. So when the ice melts, it's actually taking heat from the surroundings to melt. Does that make sense?
Yes, it does.
All right, great. And they are saying the temperature of the lime juice decreases from 29 degrees to
8 degrees.
Right. So do we understand that the final temperature of the entire solution is 8 degrees Celsius?
Yes, sir.
Okay, good. And the mass of the ice is what? What's the mass of the ice?
0.08 kg.
Right, 0.08 kg. And to find that, didn't you just divide the 80 by 1,000?
Yep.
Right, divide by 1. All right, so 0.08 kg. Great. So do we understand the basis of the question so far? Lime juice is 29 degrees Celsius. You put ice, after the ice completely melts, it reduces the temperature of the entire thing to 8 degrees Celsius. Awesome. First part, calculate the energy required to melt 80 grams of ice.
So the formula will be Q equals to LF.
Right. So you learn it as Q, right? That's fine. Q is just the heat. And E is the same thing because heat is energy, right? So then we have see the formula like this. E is equal to MLF. Right. And you understand why I'm going to use this formula, right?
Yeah.
Because if I want to melt the ice, the point at which the ice melts, what is the temperature of the ice?
Yeah, 0 degrees.
Yeah, remember we went through that just now. It makes sense, right?
Mm-hmm.
Temperature isn't going to change spontaneously. Right, water at 0 degrees Celsius, ice at 0 degrees Celsius. Right. And there's no change in temperature, so we use E is equal to MLF. Since we are dealing with the ice, we're going to use the mass of the ice. What is the mass of the ice?
0.08.
Right? What did it tell us to be the latent heat of fusion of water?
So you can just scroll up. It will be 3.4 multiplied by 10 to the power 5.
Right, Nikolai, if at any point you get confused, you'll tell me, right? You'll tell me.
Yes, sir.
All right. So, Nikolai, do you understand that if you're melting ice, the immediate point at which the ice melts, that water is going to be water at 0 degrees Celsius. Do you understand that?
Yes, sir.
It's I'm confused by that. Max, that question. When you hold ice in your hand, right? When the ice melts and you feel that water, is that water cool or hot?
It would be cool, sir.
Right. So what I'm saying is the immediate point at which the ice melts, it turns to water at 0 degrees Celsius. And for that for you to be able to heat up that water, the ice needs to melt completely. Right? So Nikolai, I'm saying that the ice needs to completely melt first before you can heat up the water. Understand?
Yes, sir.
All right. So yeah. By the way, the person that's talking, what's your name by chance?
Ashish.
Oh, Ashish.
Yeah.
Okay, good. So multiply this out for me and tell me what you get.
27,200 joules.
Right. Great. Read part B for me now.
The energy gained by the melted ice.
Right. So let's try to understand what's happening here, right? So after the ice melts, that's going to be water at 0 degrees Celsius, yeah? Let me know if you understand that.
Yes, sir.
And what was the final temperature of everything in that cup?
8 degrees.
Right. So the water at 0 degrees Celsius, right? It got heated up to what temperature?
8 degrees.
Right. That makes sense, right?
Yes, sir.
Okay. Right. So since there's a change in temperature, what formula am I going to use? Since there's a change in temperature,
It will be E equals to MC delta T.
right? Right. Now, my mass, again, I'm dealing with the ice, right? The ice. So again, that's going to be 0.08. What is the specific heat capacity of water?
4,200.
Right? Yeah, 4,200, but they're giving us as 4.2 by power 3 over here. Which is the same thing, or it's the same thing. If you wrote 4,200, that's fine. Right? And what was the change in temperature here? It went from right? So okay. Multiply that out for me and tell me what you get.
2,688 joules.
2,688.
Yep.
Let me know if that's what you got. 2,688.
Yes, sir. Yes, sir.
All right. That'll be in joules.
Yes, sir. I got that.
Nikolai, are you confused by anything that I did so far?
No, sir.
So you understand that the ice would have to melt completely first, and that took 27,200 joules. And when it's melting, the temperature isn't changing, it's 0 degrees Celsius. So it's being converted from ice to water. You understand that part, right?
Yes, sir.
And then in part B, you're actually heating up the melted ice. And the final temperature of everything was 8 degrees Celsius. So when everything was said and done, the ice water had a temperature of 8 degrees Celsius. So you understood why I use E is equal to MC delta theta. Yes or no?
Yes, sir.
Right. So, Ashish,
Yes, sir.
so bad it is, right? See if you can figure out part C.
Alright. So, the mass of the lime juice is 0.32 kg.
Mm-hmm.
The initial temp is the energy loss. So, initial temperature is 29 degrees Celsius, and the final is, so you can scroll up, please. Oh, it'll be 8. It'll be 8.
But you're gonna run into a little problem there, you know. Well, I'm not gonna tell you. See if you can figure it out for yourself.
Alright. So, the temperature change should be 21 degrees Celsius.
Yeah, the temperature change will be 21 degrees Celsius. That's correct.
Right? And the... Sir, I have to ask a question.
Ask.
So we're using specific heat capacity of water. So would the lime juice be the water here?
No. Let me ask that question. Is lime juice water?
Nah.
See the problem you run into? See the problem?
Good. Alright.
Because for you to be able to do what you was gonna do, right, you would have need to figure out, you'd have need to be given the specific heat capacity of the lime juice. Now, lime juice has a bunch of things dissolved in it, all of which would affect the specific heat capacity. So
Okay.
I feel like what a lot of students would do, they'd do what you were saying, right? And use the 4.2. I feel students would do that.
Mm-hmm.
Yeah. Let me show you how we're going to do this, right? Let me ask that question.
Uh-huh.
Ice is being placed into lime juice at a 29 degrees Celsius, right?
Right.
So where is the ice getting the energy to melt from?
Mm. Wait, so you can say what?
All right, so I'm taking the ice and I'm putting it into a cup, right? What's inside the cup?
Or the lime juice.
Right, so where is the ice getting that energy from to melt?
The lime juice.
Right. So how much energy did it take from the lime juice over here?
Right. 27,200 juice.
And how much did it take over here?
2688. So you add both and you get the total.
Yes. Right. It makes logical sense because you're taking that energy from the lime juice to melt.
Right. Okay.
Right. So the energy lost would just be equal to the sum of the 27,200, right? And the 2688.
Alright.
Right. And that would be equal to 29888 joules.
Yeah.
Yeah. But if you're okay with that.
Yes, sir.
Okay.
So, one question, right?
Talk to me.
Water. The lime juice. We were just saying it was water.
No, the lime juice is no water.
No, but in the explanation, you were just replacing the lime juice as water to just explain.
I don't think at any point in time I said that the lime juice was water.
Oh, okay. Okay.
The lime juice would not be water because the lime juice would have things dissolved in it that would either decrease or increase the specific heat capacity of the water. Right? Are you by chance confused about these examples over here?
Yes, I understand that. It's just that the energy lost by the lime juice is what I was trying to understand as well.
All right, let me explain that back for you, right? So, Nikolai, we're taking the ice cubes, right? And we're placing them in where? Where are we placing the ice cubes?
In the lime juice?
Right. The lime juice is colder than the ice or hotter than the ice?
Hotter than the ice.
So, yeah, so if that is the case, right? If that is the case, the ice is going to melt, right? Yeah?
Yes, sir.
But where is the ice getting the energy to melt from?
From the lime juice?
Exactly. Exactly. So, Nikolai, how much energy did this steal from the lime juice over here?
2,700. 27,200.
And how much did it steal from the lime juice over here?
2,688.
Right. So altogether, it took how much energy from the lime juice?
Okay, 29,888.
Honest.
Yes, sir. Yes, sir.
And Nikolai, you want to go away?
If I do, I knock over your lights.
Come on, tell them hello.
Morning,
Both everyone.
alive.
Hey, 6. I hope you feel better soon, Tevon.
I alive, you know. I ain't sick. It's just that I been feeling a little bit drowsy, you know. I lie down. All right, no, don't worry. I ain't it.
Alright. Illegal.
Should I hear Nikolai earlier today? Mom was like, not legal. Right. So yeah, Nikolai. And if you are extracting energy from our system, are you lowering the temperature or increasing the temperature? Talk to me.
Extracting, you say?
If you're taking energy and you're pulling it away from our system,
You would be lowering it?
yeah, you'll be lowering the temperature. Because okay, remember the kinetic theory of matter, it said that if you apply heat energy, it would add kinetic energy to the particles and they would vibrate and move out more regular speed. They
Yes,
will
sir.
vibrate and move about more vigorously or vigorously. So if you do the opposite, right? If you actually extract energy from a system, you are taking kinetic energy away, right? And you are decreasing the amount of vibrations. So, Nikolai, what I'm saying is, if you take energy away from a system, you'll make the system cooler. And can you see that that's what happened over here?
Yes, sir.
Yeah. Ashish, it's making real sense, right? You know why it went from 29 to 8, because we
Yeah.
actually pull the energy away from the lime juice, so we decrease the energy. Make sense?
Yes, sir.
All right, so see if you can figure out part D now.
Specific hit.
So
Sir,
this is what you was on about. This is what you was, talking.
sir. If, so just tell me if I'm going on the right foot. And the energy lost by lime juice, it will be gained by the ice, because if energy lost by the ice, it will be gained by lime juice.
Yes.
Right. Okay. So you can scroll up. Just like zoom out, please. Right. We are the total there. Right, sir. So, so right. So we could write Q equals to MC delta T.
Right, so yeah, I'm gonna write E is equal to MC delta T, same thing. MC delta theta, same thing.
Yeah. So now we could substitute mass is 0.32 kilograms.
Right?
C unknown. Okay, C unknown.
Right, so let me just write down everything we know, right?
Yeah.
We know the total energy, right? Lost by the lime juice. Talk to me. Do we have the energy?
Yes, sir.
Right, so the energy, right, is equal to 29888, yeah?
Yep.
Right, so we have energy. Do we have mass of the lime juice?
Yeah, 0.32.
And do we know the change in temperature?
21.
Right? What was the only unknown there?
C.
Right, so to find for C, we could divide both sides by M delta theta.
Right.
So let's do that real fast. If I divide by M delta theta, it's gonna leave me with C on the right hand side. So the formula for C is just E all over M delta theta.
Right.
I know what my energy lost by the lime juice was, right? Remember, specific heat capacity isn't just how much energy it would take to raise the temperature. It's just how much energy you would need to change the temperature. So a change could be a negative change, like a drop.
Yeah.
A rise. So in this case, the temperature dropped, right?
Right, sir.
Energy that it took to drop was 29,800 units.
Right.
So in other words, the energy it took for the temperature to drop, right? You can calculate the specific heat capacity from there. Because this is the energy it took for this temperature here to drop from 29 to 8. Understand?
Right. So, sir, it will be 29,888 divided by 0.32 multiplied by change. So, it will be 0.32 multiplied by 21.
21, yeah.
Right. Got you, eh?
All right, so let me know where you get for the answer.
4445 J kg minus 1 C minus 1.
Sir, I have 4,447.61.
Have that as well.
Right.
Yeah, I have 4447.619048.
Oh, sir, yeah, all right. Yeah, I'll do something wrong. Sorry.
That's all right. Right, so that would be 4447.62, right? the units are going to be joules, right, per kg, degrees Celsius.
Yeah.
I didn't convert my temperature to Kelvin, so I'll leave it as degrees Celsius. Understand?
Yep.
Right? And if I wanted to write my answer in, say, standard form, how would I do that?
It will be 4.4 multiplied by 10 to the power 3 G divided by kg degrees Celsius.
Yep. Sound like he's our physics boss.
Nah, sir. I try nothing.
Well, it sound like you like physics at least.
Yeah.
Oh, wait till we do the electrical part of physics. Oh, I love it. Well, I do in electrical engineering, eh? I do my bachelor's in electrical and computer engineering. So obviously I go like the electrical parts. I love the electrical parts.
Yeah.
Looking forward to that part. But also, my second favorite topic is thermal physics. Right? Let me know if you understand this. Nikolai, talk to me, Nikolai. Let me know if you understand this.
So the 21 was in the question above.
Yes. So check this, right? If we want to figure out the specific heat capacity of the lime juice, right? We need to know what E is, we need to know what M is, and we need to know what delta theta is. So that's just a change in temperature. So initially the lime juice was 29 degrees Celsius, but after everything, it dropped down to 8 degrees Celsius. So what was the change in temperature there?
21, sir.
Right, 21 degrees Celsius. You okay with that?
Yes, sir.
Okay, wood. Right, wood. Right. Right. So while we on this topic, I want to look at the passive properties of materials, and I want to look at the greenhouse effect after. So guys, I want to take a screenshot of this. Take a screenshot of this.
So this look like you make this yourself?
This is AI. I'll be real honest. I
Oh,
just tell the AI what I wanted. Yeah,
okay, sir.
I don't lie. But I made it give me very specific things. So make sure you have a screenshot of this, right? As soon
Yes,
as
sir.
you let me know. Right.
Wait, so one question, sir. These materials here, this is mostly what does come in the exam that they
Yeah,
would ask about.
yeah, everything we do in here is what could potentially come in the exam. Right? Yeah. So just off the top of your head, right? Which color do you think absorbs the most heat?
Black.
Which color? It's one now, which color?
A color that. Oh, nah, I brown skin. I just like use black.
Oh, oh,
I mix so I know in Edo some races.
oh, buklat. Hey, right? So if we're talking about the best absorbers, then black materials will be the best absorbers of heat. We know that, right? And black, and when you wear black on a hot day, it just feel real hot.
Yeah, real.
Yeah, because the black cloth is absorbing most of the heat from the sun, right? So great absorbers. Right now, absorbers are also good emitters, right? So black is also a great emitter of heat. I do not want you to confuse emittance with reflectance. Don't confuse them, right? Emitting heat is simply giving off heat. Reflecting heat is okay. If you're reflecting heat, you're not absorbing it or anything. You're just sending it back in the direction it come from, right? So, Nikolai, if we just said that black surfaces are great absorbers of heat, wouldn't they absorb a lot of thermal energy?
Yes, sir.
If you touch, imagine you had a black surface on a very hot day. And if you go close to the black surface, you'd feel the heat radiating the black surface.
Yes, sir.
Right. So that radiation is synonymous with emittance. So whenever you hear the word emitter, it talks about, okay, how much heat does that object give off? So since black could absorb so much heat, it could also give off a good bit of heat. I'm gonna know if you understand that.
Yes, sir.
Ashish, you understand what I'm saying?
Yes, sir. Yes, sir.
So do you understand that emittance and reflectance are not the same thing?
Yes, sir.
Okay, again, emittance is an object's ability to radiate heat or emit heat, to give off heat. If something is reflecting heat, then it's not absorbing the heat, it's just simply sending the heat waves in another direction.
Right. I understand.
So it's not emitting the heat, it's just reflecting the heat. Right. Okay, so white surfaces now, and black surfaces are very poor reflectors. And it makes sense, right? If it's poor reflectors, and they will absorb most of the heat.
Yes, sir.
Right. Let's look at white surfaces now. White surfaces are, do you think white surfaces are great absorbers or really bad absorbers?
Bad observer, sir.
Because they reflect most of the heat waves, right?
Yes,
So,
sir. They're just like the opposite.
right. So great reflectors, right? Poor absorber, right? And poor emitter. Do we understand what I'm saying here, guys? Do you understand this?
Yes, sir.
So, Ashish, if I ask you what emittance is, are you going to tell me it's the same thing as reflectance?
No.
No. Emittance is just the ability for an object to absorb heat and give it off. Does that make sense? You understand that? All right. I'm going to take it that you'll understand this, right?
Yes, sir.
Okay. Let's talk about dull surfaces now. Do you think dull surfaces are good reflectors or bad reflectors?
Bad reflectors.
Right. They are bad reflectors. And if they are bad reflectors, chances are they are a great one.
Absorbers and emitters.
Absorbers and
Oh, great. Stefan, what killing you so, boy? Hey, this man laughing, giggling. You're good? Look at that. Right. So if we're talking about a shiny surface, right? A shiny surface. A shiny surface is a great what?
reflector.
Right. And like, oh God, guys, what am I rather do? Show you what? I'm rather show you what?
Show you
Reflection.
touching yourself
Right.
or something.
A mirror is a good example of a shiny surface. So shiny surface are good reflectors, right? But they are poor what?
Absorbers and emitters.
Yep.
Right. So I think everybody understands the general passive properties, right? How you feel about this?
Feel good, sir.
Okay, good. So does everybody, I can't stress this enough. Do you understand that the more heat something has and the more heat it has absorbed, the more amount of heat it be able to dish out?
Yes, sir.
Okay, good.
Yes.
I can't stress that enough, right? Right. I write so neat here. I don't want to erase it, but oof, I erase it. I write so neat there. Okay. Ashish, you help me with part one, and then Nikolai, you help me with part two, right? So Ashish, give it a read for me.
4 factors of the surface of a material on which the absorption and emission of radiation depend are texture, rough or smooth, rather shiny, color, black or white, area, large or small. State with a reason the appropriate characteristics of two of the above factors in design of one, a car radiator.
Right. You're making a car radiator, right? Wouldn't you want it to take as much heat as it can from the engine,
Mm-hmm.
right? So you'd want it to be a good what?
I got a absorber.
Right. So you tell me, what should I use to make the car radiator?
Say break up, I can never say.
What characteristics should I use in my car radiator design?
Oh, well, it should be a good absorber, so it should be um uh what? Is a good absorber, so it should be black.
Yeah, it should be a black surface. Right?
And so the area should be large.
Right? The area should be large as well. Yes, you can say that. But I think a more obvious one would have to be
In
it-
nature.
yeah, like okay, it have multiple answers here, right? If you want to make a car radiator, number one, the texture should be rough, right? Because you want it to absorb heat. Yeah,
Right.
Yes, sir.
nature, it should be dull because again, you want it to absorb heat from the engine, right?
Mm-hmm.
Color, it should be black because you want it to absorb heat from the engine. And area, you want it to be a large surface area so it would absorb heat. So anyone, if you mention any of those, you're fine, right? You're fine. Are you understand that?
Yes, sir.
Yeah.
So I'm gonna say black surface, right? And dull surface.
Excuse, sir.
Yeah.
Why I born in AC, sir?
I'm confused.
Because I can't take heat so much.
Because it does absorb heat.
No, they say for the melanin, well, I gone into biology, sir. It's based on your skin. So the more darker it is, the more heat you absorb.
Right?
So I'm not of the black syndrome. I'm more in the brown, but I still don't like the heat. So that's why I say I born in AC.
Oh. So one, you want to laugh? Oh, all right, so are you okay with this, right? So you can say black surface, dull surface, rough surface, and large surface area. Are you okay with these answers?
Yes, sir.
Okay, great. But you just wanted two, right? And you need to say a reason. So let me just say a reason for the black surface, right? Black is a good right? Black is a good absorber and emitter of heat. As such, it extracts heat energy away from the engine and emit it to the surroundings. Right? Do we understand that reasoning? I mean, if you guys okay with that,
Yes, sir.
right? And for any of these three, you could just say, well, better emitters of heat. Right? Because guys, your main objective, right? Your main objective is to absorb the heat from the engine and emit it to the surroundings. So you guys understand that, right?
Yes, sir.
Yes, sir.
Right, the roof of a Caribbean home. You want your home to get hot or not?
You want it cool, sir?
So do you want to absorb the heat or reflect the heat?
Reflect.
Right. So I'm going to use a white surface. All right. Why? Because white surfaces, they would reflect visible, right, and infrared radiation. For those of you guys that don't know, heat is carried in infrared radiation, right?
Yes, sir.
And shiny, I would say shiny, right? Because shiny, good. Right? Good reflector, right? Reflects even more. All right, so are we okay with the answers for this question?
Yes, sir.
All right, so the next thing I want to move on to, oh, look at our question here. Suppose we could do this question one time. Because that was partly.
Yes, sir.
Yeah, Nikolai, get the question I read for me.
The following data were observed in an experiment using an emission heater to determine the specific latent heat of vaporization of water. Mass of can and water at start of boiling, M1 equals 0.28 kilograms. Mass of can and water at end of boiling, M2 equals to 0.26 kilograms. Power of heater equals to 150 watts. Time of heating is equal to 5 minutes. Using the data above, calculate the specific latent heat of vaporization of water, assuming a neglecting.
Negligible.
Sorry, sir. Negligible. Yeah, that would, sir. Heat is lost to the surroundings.
It have this one meme with this guy, like, you know what I'm talking about?
Who does start all that, sir?
No, it had this like one meme with this guy with a mustache, and he was like, if I find the meme, I will share. I'll find it, I will share, right?
Yes, sir.
But try saying the word negligible.
Negligible.
You should have like a Korean person. Or some like a Japanese person. I don't know. I hear some like Korean or Japanese or something. But yeah, you say it properly, right? So we want to figure out the specific latent heat of vaporization. Can somebody just remind me what the definition for specific latent heat of vaporization is?
That is the amount of heat required to raise 1 kilogram of a substance from solid to liquid without the change of temperature.
It sounded like it was partially correct.
Yes, sir, because I put in temperature and then it's not supposed to have temperature.
And then
Without the temperature.
yeah, you're supposed to say is the amount of heat energy required to convert 1 kg of a substance from a liquid to a gas or a gas to a liquid. Right?
Yes, sir.
Right. So first things first, can you tell me what the formula for specific latent heat of vaporization is?
E is equals to MLV.
Right? E is equal to MLV. Awesome. So I have a question, right? If I have a mass of can and water at start of boiling, and then I have mass of can and water at end of boiling. When I boil water, what is happening there? If I boil water, what is the water turning to?
The water is turning to gas, sir.
Right. If I am boiling, it's turning from water to what?
To gas.
What's the specific name? Like when we deal with water, you would say water to?
Vapor.
No, it's a steam. Steam. Right?
Yes, sir.
So is it possible for me to figure out the mass of steam?
Yes, sir, from subtracting it to the mass of can and water at the end from the starting and the end.
So I would say M2 minus, so I'd say M1 minus M2, right?
Yes, sir.
Because guys, do you understand that we are losing some water because we're boiling, and when you boil something, you lose some of the mass because it turns to steam. Easy?
Yes, sir.
Oh, good. So mass of steam, that would just be equal to that'll be M1 minus M2, which is just simply 0.28 kg minus 0.26 kg. What am I going to get?
0.02, sir.
Can I get 0.02 kg? Good. All right, so here this, guys, here this. If we want to figure out the specific latent heat of vaporization, well, we clearly want to figure out LV, right? This is what we want to figure out.
Yes, sir.
Right, this is what we want to figure out. So how would I make LV the subject of the formula?
Dividing it, sir.
I would have to divide both sides by what?
M.
Right. So the latent heat of vaporization, LV, is just E all over M, or the specific latent heat of vaporization, right?
Yes, sir.
All right, guys. We know what the mass is, right? Yeah, as you know what the mass is?
Yes, sir.
Right. The only thing we are missing in this formula is the what?
The energy, the
Energy.
E.
We're missing E. Now, my advice would be they gave us power and they gave us time. Is there any formula that you could think of that has power and time in it?
Yes, sir.
Power is equal to what?
Energy over time.
So if I want to make energy the subject of the formula, what do I have to do on both sides?
Multiply.
Multiply by what? I want this to cancel off. So I need to multiply.
By T.
Right. So energy would be equal to power by time. You understand that?
Yes, sir.
And the thing is, right? Do we know what the power and time is?
Yes, sir.
What's the power?
150 watts, sir.
What's the time?
5 minutes.
Right, but is minutes the SI unit for time?
No, sir.
What's the SI unit for time?
Seconds, sir.
How would I convert 5 minutes to seconds?
Multiply by 5 by 60, sir.
Right, 5 by 60. And that would be equal to 300 seconds. So multiply that out and tell me what you're getting.
I got 45,000, sir.
Yeah, that's correct. Ashish, you're following?
Yes, sir.
Right, so we have the energy and we have the mass now. How am I going to find LV?
Divide the energy by the mass, sir.
So my energy is 45,000 divided by my mass, which is 0.02.
2.2 times 10 to the power 6, sir.
2.25
Yes, sir. Well,
Yes.
2.25.
by 10 to the power 6, right?
Yes, sir, because that's a real big number.
Right. And the units would be energy is joules and mass is kg, right? So joules per kg. Let me know if you understand that.
Yes, sir.
Right. Now, guys, is there a prefix I could use for 10 to the power 6?
Mega.
Yeah. So if you want to get right, it is 2.25, right? Mega joules per kg. But if you leave it like this, then it's fine. I just say like how extra you could do.
Okay, sir.
Right. Does everybody understand that?
Yes, sir.
But how do I easy question?
Easy, sir.
Okay, good, good. Right. Ashish, read this question for me.
The coil of the immersion heater was not completely submerged. Explain how this would have affected the value for the specific latent heat of vaporization obtained in B on page 17.
So if it wasn't completely submerged, right? And it was kind of inefficient, and you would lose a good bit of the heat in the atmosphere.
Yes, sir.
Yeah. So if that was the case, and a lot more energy, and the heater would have had to supply a lot more energy to convert it from liquid to steam, because here was saying, right? Here was saying, if it wasn't completely submerged, a lot more energy is going to have to be used. Why? Because the entire thing is not submerged. A good bit of the energy is actually being lost. So if you're actually measuring how much power is being used, a lot of power is going to be used. I wonder if you understand what I'm saying.
Yeah.
So I'll say it one more time, right? If it's not completely submerged, will all of the power be used in converting the liquid to steam?
Yeah.
No. Here I'll say it again, right? If you don't completely submerge, if the coil of the immersion heater isn't completely submerged, right? Remember, the coil is what's going to generate the heat, right?
Right.
If the coil isn't fully in the immersion heater, is all of my heat being used to convert liquid to steam, or is some of it being wasted?
Um. Some would be used, but most could be wasted.
Yeah, because if the coil isn't completely in the water, right? And some of the coil will be exposed to the atmosphere.
Yeah.
So wouldn't some of my okay, so wouldn't I lose a good bit of my heat then?
Right. Right. Yeah.
So if
Cause
you're recording, so if you actually recording how much power is being used, and you would take and you would any reading would show a large amount of power to do the same thing because it's not actually fully submerged.
yep.
Yeah. So if I wait, do you understand that if it was fully submerged, would I use less power?
Yeah. Cause some of the energy was lost heat in the coil and surroundings.
Right. And if the coil was submerged in the water itself, then all the energy would be all of the energy would be supplied to the heat in the water. I mean, if you understand that.
Right. Yeah, sir.
And just by looking at this, right? Power, if the power increases, my energy would increase. And if my energy increases, my latent heat of vaporization would drop or rise.
It will increase.
Yeah,
Wait, no. Oh yeah.
it would increase. Let me run it back one more time, right? Since the coil is not completely submerged, and more power would have to be used than necessary.
Yeah.
Because you understand that it's kind of inefficient because it's not actually the full coil isn't in the water, right? If the
Right.
coil was in the water, it would take less power because all of that energy would be transmitted to the water. You understand?
I understand.
But because it's not fully submerged, you're actually losing a good bit of that power, right?
Right.
So what you would notice is plenty power is being used up, right? To do the same thing that would have used less power if it was fully submerged. So do you understand by the coil not being fully submerged, more power is going to actually be used to do this?
Yes, sir.
Right.
Yes.
So if more power is being used, right? So my power would get bigger, right? My value for power would get bigger. What would happen to my energy value? Would it get smaller or bigger?
It will get bigger.
Right. And look at where energy is. It's in the numerator. If the
Mm-hmm.
numerator gets bigger, what's going to happen to the total value for latent heat of vaporization?
It will get bigger.
Exactly. So by the coil not being fully immersed, the value is going to be larger than it should be because a lot of energy is being wasted. So you'll have to use a lot more to get the same result. Understand?
Right. Yes, sir.
Right. It would. There's one thing I hate writing answers with like words. Oh, what should I gotta say it out loud, but you write it is like
Real.
it would raise the value since heat energy required Same. Water. Right, so it would raise the value since more heat energy would be required to convert the same mass of water from liquid to gas. Right, so you guys understand my reasoning? Let me know if you understand the reasoning. Yeah or nah?
Yes, sir. Yes, sir.
So Nikolai, I was gonna say Nicolette just now. Remember what he's doing to Roman?
Yes, sir.
You remember what he's doing to Roman? It's about So Nikolai, if the coil isn't fully submerged, do you understand that the coil is actually what's doing the heating?
Yes, sir.
So okay, you have an electric kettle.
No, sir.
Oh, if you had an electric kettle, you would get exactly what I'm talking about. How the electric kettles work is that, and it would have like an electric coil over here, and this is be plugged into the wall, right?
Okay.
And what has happened is the wall outlets would provide energy, and that would heat up the coil. So my question is, right? If this is water, right? And some of the water is not only some of the water is touching the coil. Do you think that would be an efficient process?
Yes, sir.
No. However, if the entire coil was submerged, would that be an efficient process?
Yes, sir.
So here what I'm saying, right, Nikolai? I'm saying that if the coil is partially immersed in the fluid, it's going to be a very inefficient process and a lot more power is going to be used than is necessary. So Nikolai, I'm saying that if the power increases, right, my energy is going to increase. And if my energy is going to increase, then my latent heat of vaporization is also going to increase. So do you understand?
Yes, sir.
So now that I visualize it and I know how electric kettle is, it making sense now.
It would.
They would.
That's good.
He does.
All right. So here what? Let me just do this question here. Right, so I'm gonna do this question, right? A cooling curve and a heating curve. And then I'm going to move on to this greenhouse effect question, and that'll be it for the night. Tomorrow we're gonna look at gas laws. Are we okay with everything so far?
Yes, sir.
Good. Oh, by the way, all I need to know about thermometers, eh? Just saying that. So like, I'll like to take a
Hey,
picture.
no, let me hear thermometers.
Yeah, take a screenshot of this. You need to know the adaptations of a thermometer and like the range of a thermometer and the specific adaptations. So take a screenshot of this to know this. You also need to know about thermal expansion, by the way.
Oh, okay, sir.
So take a screenshot of this, right? Right, and take a screenshot of this.
Right, sir.
All right, good. So let me do this question here. All right, so Ashish, you got a question I'll read from that.
A substance which has a melting point of 80 degrees Celsius is cooled from 90 degrees to a complete solid at its melting point. Sketch a graph in figure 1 to represent the statement above.
All right, so it's cooled from what temperature? What temperature is it cooled from?
90 degrees.
Right, so my highest temperature is going to be what?
90.
Right? And my coolest temperature is going to be what?
80.
Not quite.
What's that?
Not quite. It's actually cooled to a complete solid. So let me show you how it's going to look like, right? So 90, then we have 80 over here. So if 80 degrees is its melting point, right? Then at 90 degrees, do you think it's a liquid or a solid?
If it's cooled, I mean, it'll be a solid.
Now here what I'm saying again, right? It has a melting point of 80 degrees Celsius, right? So if it has a melting point of 80 degrees Celsius, if I go past that, would it be a solid or a liquid?
Oh, it'll be a liquid. It'll be a liquid.
Right, because I would have went past the melting.
Okay.
So I'm cooling from 90. If we're looking at 90 degrees Celsius, that is past the melting point. So what would the state be of the substance?
It will be from a liquid to a solid.
Right. So let me show you how this is going to work out, right? Remember, when you are changing state, there's a period over which there's no change in temperature, remember?
Mm-hmm.
Right. Latent heat fusion. Right. You know what I'm talking about?
Yep.
So watch how it's going to look, right? So a cooling, right? When I hit the melting point, this is what's going to happen. It's going to be flat. Do you know why it's going to be flat?
Because no temperature change.
Right, because right now, energy is being expended on changing the molecular structure from a liquid to
solid.
Right. And when it turns to a solid, now I'm going to cool it completely. So let's try to run through what's happening here. So over here, it's a liquid. Over here, it's actually going from a liquid to a
solid.
Right. And Nikolai, what is it over here?
Repeat, sir?
Yeah, what is it over here, Nikolai? What is it over there?
Solid, sir?
Yeah. So Nikolai, let's try to understand this one more time, right? So they're saying you have a substance with a melting point of 80. So Nikolai, if I go past the melting point, would it be a liquid or a solid?
It'll be a solid.
Now let me try to understand that, right? Let me try to understand that. What happens at the melting point?
What do you mean? Like, read the question?
No, like just in general, think of matter, right?
Yeah.
If I tell you a solid is melting, the solid is turning into what?
The liquid.
Right. So if the melting point of something is 80, if I go past 80 degrees Celsius, would the substance be a liquid or a solid?
It'd be a liquid.
Exactly, because until I'm going past the melting point.
Yes, sir.
Right. So I'm cooling something from 90 degrees Celsius to a complete solid, at its melting point. Right, so you understand what happened in here?
Yes, sir.
So in other words, you start off at 90 and you start cooling it, right? You start cooling it. Right?
Yes, sir.
Now, when it reaches the melting point, the temperature is not going to change. Do you know why?
Because we reach at its melting point.
Not just that. Remind me, what is the latent heat of fusion say?
It changes the kilogram of substance from solid to liquid.
Right. So, Nikolai, what is happening over here, right? This is a period in which the atomic structure is being rearranged from a liquid to a solid. And the point at which that's happening, there's no change in temperature. There's no change in temperature. That's why it's a flat line, right? And then I continue to cool it. And this region over here would represent a solid. Let me know if you understand that.
Yes, sir.
So it's a liquid over here. It going from a liquid to a solid, right? And over here, it's a complete solid. Do you feel okay with that?
Yeah, I feel okay with that, sir.
Right, and this is called a cooling curve. Right here, what? Let's look at the the heating curve for this as well. All right, so Nikolai, yeah?
Yeah, yes, sir.
All right, what if now I told you that um okay, watch, I'm gonna flip the rows now, right? Let's just say a substance is at 0 degrees Celsius. It is heated to 150 degrees Celsius. If its melting point is 70 degrees Celsius, draw the heating curve. Right, so Nikolai, what's the initial temperature of the substance?
0 degrees Celsius.
And at 0 degrees Celsius is a solid or liquid?
Solid.
All right. And I am doing what to it?
You're melting it to 150 degrees Celsius.
Right, what is the melting point?
70 degrees, sir.
So at 70 degrees Celsius, what's gonna happen? So all over here, it's actually a what? A solid or liquid?
Solid.
Okay, what's gonna happen at this point?
It will change in phase. It will change phases from solid to liquid.
And that'll be a flat line, right?
Yes, sir.
And then we'll proceed to go up to what temperature?
To 150 degrees.
Great. So this is solid. This is solid to liquid. And what is this?
Liquid.
Right, this is liquid. Okay, great. So guys, Ashish and Nikolai, are you all okay with cooling curves and heating curves now?
Yes, sir.
Yes, sir.
And if I then told you that the boiling point is at 200 degrees Celsius, then what would happen is this would proceed to 200, it would flatline, and then it would continue going up. And this phase change here would be from liquid to gas. Do we understand that?
Yes, sir.
Okay, good. You need to be familiar with cooling curves and heating curves, right? Right. So, Nikolai, read part C for me.
A physicist converted 2 kilograms of water at 37 degrees Celsius to steam at 100 degrees Celsius. Assuming no heat is lost, calculate the amount of energy needed to heat the water at 100 degrees Celsius.
All right, so Nikolai, let me try to understand what's happening here, right? So, initially, what is the temperature of the water?
0.
Now, read that back again,
37 degrees Celsius, my bad.
right? And we want to convert that to?
Steam,
Now, before you could go from water to steam, you first have to heat the water to what temperature?
100 degrees Celsius.
Right. So you're going to heat the water to 100 degrees Celsius. And then you would need energy to rearrange the molecular structure to go from water to what?
Gas or vapor or steam.
Right? Do we understand that?
Yes, sir.
So when I think I should get them some thermodynamics. Wait, sir. I want to do some thermodynamics.
It's the same thing, but legally structured.
This thing only looking hard, you know, but like it's actually simple.
Simple with a lot of steps.
Exactly.
Yeah, but it's just simple. Yeah, boy.
This is your physics.
That's actually what we had to do for our exam.
Yeah, this is one of the courses.
Damn. That is a lot. With
What?
That's a whole mixture, boy. Physics and maths, boy.
This man get 90 by you.
Oh, I get 93. 93? Yeah,
And
93.
he's specifying he marks too, eh?
But I will tell you something. And the first time I write the course, I get 25. I don't know how. I get 25. And the second time I write it, I get 93. Yeah.
Hey, come back.
Yeah, that sound like cheating, but I wouldn't say so.
No. If you think that is cheat, right? I think that I don't know how I do that, but like I know my stuff. I got in physics. I got in like thermal physics and whatnot. Like they tell you, the first time I write the exam, I get 0.1 out of 15. Like I was like, what? How? How? And then this time I write it back, I get 15 out of 15. Don't understand. I don't understand. I
Practice, I guess.
said that again.
Practice.
I just do work before the exam and get 15 out of 15.
I tell you what, we study the day before the exam, legit the day before. You know, the whole syllabus the day before. This man get 90 something. I pass. That's all I need.
Yeah, we wouldn't talk about the marks, we pass.
Hey, man,
Pass.
man pass. The man pass.
A pass is a pass.
Exactly. Yeah. But I didn't electrical engineering, eh? This is stuff that you would do if you do mechanical engineering. This is mechanical engineering stuff, not electrical engineering stuff.
So I want to do okay.
Well, it's a preview now.
I wouldn't lie, it's fun, eh? It's fun. Like I actually enjoyed it. The second time I wrote it back.
So I was expecting it to be hard, but that looking way past hard.
No,
Something-
Easy.
it's actually very simple.
They're really easy.
It's actually very simple.
Really.
It's like the same steps as this, but just on a higher level. Right, but let me continue.
If I telling you it easy, it easier. If
Illegal.
I saying that illegal.
It is legal. Right. So let me finish up this question, move on to the greenhouse effect question, and that'll be it for the night. We essentially wrap up with thermal physics. So when I come back, okay, I'm not sure I'm gonna have a session tomorrow because tomorrow most likely we'll want to have a math session. Yeah.
You know how much things you're doing tomorrow?
I'll think doing tomorrow, boy. Yeah, boy.
Doing something in the morning.
In the morning. Well, we're going up
Something in the morning.
now. Well, we're going up with you in the evening, like in the morning.
Yeah, somewhere.
Something around that time. And well,
And then he can come back and do a photo for maths.
What is the time you just say?
Huh?
What is the time you just say?
Photo for 12,
Alright.
12-hour session of maths.
No scene. Idea.
he always there.
Yeah, how is he?
He always
How is
Nikolai is the number
he? He
one.
have to day, otherwise we finding you.
Whoa. He finding you.
Yeah, I finding you. I don't know where you live. I just right here.
Whoa.
Yeah, you go either use Google Maps or Wiz.
I using both.
Whoa.
If one down, I use the next one. I ain't slacking him.
Oh yeah. Tavon is he's my debt collector,
I see FBI.
FBI bodyguard. The what? I don't know.
CIA.
Or the Men in Black.
Hey, boy. No, forget man in black. Man is black. Hey, that was a good one.
Quite funny.
That was a good one. That was a good one.
We
Next thing people think I just say one and I cool. We not digging no horrors by them kind of jokes. It's fine. Feel like
Editor, remove that part.
man is black. We
I don't mean anything by it. I genuinely don't.
Yes,
No.
sir. We all know. We all know. It's just jokes for joking.
Next thing somebody clipped out and say I racist. Boy. The
Yeah,
opposite.
sir. They gotta face all that we said.
They want to find them.
Them can't be one whistle on John to tea. Them can never do that.
Right. Are you listening fast? So Nikolai, going from water to the 7 to water to 100. What formula are you using?
Formula.
Yeah, formula.
So the way out, me just thinking, I thought we were just adding it to.
Nah,
No, no, it was just a thought, no, sir. It was just a thought.
I don't need to. Well, yeah, you would have to add this. You'd have to add the energy over here and the energy over here. Sure. But over here, they want us to figure out the amount of energy needed to go heat the water to 100. So you're going from water to the 7 degrees to water to 100. So
That's the energy equals MC changing temperature.
I'd see like the thermo, like in thermodynamics, you'd actually write the differential. You'd say the theta.
Okay.
Show them that and I feeling pumped or feeling like,
you want to do October again?
yeah, boy.
That was it's not that hard enough, but for me that was for us who crammed down in one day.
That not even gonna take a day for me. That's gonna take like weeks. All
No.
that I remember. And more.
No, and it's a pattern recognition. Once you understand the pattern, it's key.
Mm-hmm.
And that was just like one question or one question with parts.
That one question. Well, yeah, one question.
This is one question
With parts.
with parts. This is one part. This is one part.
They might have up to 7 parts for that one question.
That's basically like the whole paper.
And we have 2 hours to answer what, like 4 or 5 questions?
Yes, similar to that with like multiple parts.
Yeah.
Not that much, probably like around 2, but that one was the one with the most parts.
I'm
7.
telling you, that sound like cheat. You telling me 2 hours to just solve 4 or 5 questions with a whole set of parts.
Yeah.
And I finished the exam, eh?
This one finished with 30 minutes remaining.
Yeah.
30 with all them thing?
I don't know how, eh?
I tell this man, super boy. I remember the time and this man finished with 30 minutes remaining.
Hey, if I was doing that same thing, I'd have sit down next to you. Yes, people fancy.
You wish? I try to sit down next to this man. I reach up 4 seats in front and 9.
I was looking for you. I was looking for you. I was like, where this man in the exam, boy?
I was like 9 seats in front of this man.
Yeah, boy, let me continue. So the mass is 2 kg, right? The specific capacity is 4,200. And the change in temperature is 63. How I get 63? Well, 100 minus 37. You get 63, right?
Yes, sir.
So multiply this out on the way again.
I get 5.29200. Well,
I supposed to get
no, I get 529,200, but I was put it in the times 10 to the power, no, sir.
if you're trying to do that, that'll be 1, 2, 3, 4, 5. That'll be 5.29 by 10 to the power 1, 2, 3, 10 to the power 5. But leave it like this.
We just leave out the 2.
Well, I round it off to 2 decimal places.
Oh, okay.
Yeah, so if I have 5.292, I'll just be 5.29. I'm going to leave it like this, right?
Yes, sir.
Right. Okay, now to heat the water from 100 degrees Celsius, look, the real help you out here, you know. Watch. They said from 100 degrees Celsius to steam at 100 degrees Celsius. So over here, there's no change in temperature. No change in temperature. There's none. You see now, right? So what formula to use?
That is E equals mLV because it's steam.
Yep, you are correct. E is equal to MLV. Right. So the mass again is 2, right? And the latent heat of vaporization is 2.3 by 10 to the power 6. Right? You should get 4.6 by 10 to the power 6.
Yes, sir. That's what I get.
Right? And if you want, you could write a prefix. You could say 4.6 megajoules. That's optional. Are you okay with that?
Yes, sir.
Right? Now they're asking us to completely convert the water from 37 to steam at 100. So guys, didn't I just calculate this and this?
Yes, sir.
If I want to find the total energy, I would just have to add up these parts. So
So
add up that from on some way again. Say that about 4.6 megajoules and 529,200. And let me know way again.
I got 5129200.
Are you okay with that?
Yes, sir.
Mm-hmm.
And to get that, I would have just add 4.6 megajoules. So I could just write 4.6 by 10 to the power 6 plus the 529,200. Right? Great. Guys, we getting that 15 marks in the exam or?
Yes, sir.
And it's light.
Right, this is easy, right? Easy. Easy work, light work, light work. So, if we look at this now, I'm feeling lazy to write, so I'm just going to leave this over here, but I'll explain the concept to you all in very explicit detail.
Sir, I remember I do a question like that and I had it in simpler terms.
I wanted to give all a real proper answer, right? And if you're going to keep physics, you'll see Planck's equation and whatnot. This is extra knowledge. It's good to know, right? You'll see it if you do Unit 1 physics.
Okay.
But let me explain what's happening here, right? First things first, Ashish, get the question I read.
Figure 7 shows a section of a solar water heater which utilizes the greenhouse or glasshouse effect in its operation. Figure 7, section of a solar water heater. 1. Briefly describe the greenhouse or glasshouse effect.
All right. So let me explain something, right? The sun, right? I have the sun here. Do you think the sun emits a lot of heat?
Mm-hmm.
Yeah, it does. Now, what kind of rays do you think the sun emits?
Infrared.
It emits infrared and visible light, right? But long story short, the sun emits short wavelength radiation. So infrared and visible, short wavelength radiation, right? Mainly infrared, short wavelength radiation. All right. So a little bit more, right? Short wavelength radiation.
Yes, sir.
And could everybody agree that the sun is going to emit a very large amount of infrared radiation? Infrared radiation is a specific type of radiation. If you didn't know, heat is transmitted via IR radiation, right? Infrared. So the sun is going to emit short wavelength radiation at a very high intensity. Now, the short wavelength radiation has a very high penetrative ability. Has a very high penetrative ability, and it has very high energy. All right, so are you all with me? You understand what I'm saying?
Yes, sir.
Right. So Ashish, the sun emits what type of radiation? Long wavelength or short wavelength radiation?
Short wavelength.
In the form of?
Heat.
In the form of infrared radiation, right? Infrared. Infrared waves or infrared radiation. I should probably say infrared waves. Yeah. Right. Let me know if you understand that.
Yes, sir.
Right. So I'm saying that the short wavelength radiation has a very high penetrative ability and it has high energy. So what's going to happen, right, is that the short wavelength radiation emitted by the sun is going to easily pass through the glass plate and is going to hit the black collector plate, right? You with me?
Yes, sir.
All right. Now, I just said that short wavelength radiation has a high or low penetrative ability.
High penetrative.
Yeah, so that passing through the glass plate like nothing, right? Now, when that is the case, when that happens, right, doesn't the short wavelength radiation hit the black collector plate and heat it up?
Yeah.
Yeah.
Black is all good. Yeah.
Right, so it's gonna get hot, right? Indicated by the red line over here. It's supposed to get hot, right?
Yes, sir.
Now I have a question, guys. The black collector plate, yes, it's gonna get hot, right? Yes, it's gonna get hot, right?
Yes, sir.
Yes, sir.
Is it going to get as hot as the surface of the sun?
Nah.
No.
Yeah.
We know it's a good absorber and a good emitter of heat, but answer that question. It's gonna get hot, right? And if something gets hot, wouldn't it emit heat? If something gets hot, wouldn't it emit heat? Wouldn't it radiate heat?
Yes, sir.
Sir.
But what I'm asking is, yes, the black surface is gonna get hot, but it's not gonna radiate as much heat as the sun. So you're gonna see little waves over here of heat being radiated, right? Now, can we all agree that most of the energy is going to be absorbed by the black collector plate? Yes or no?
Yes, sir.
So only a very little amount of energy is going to be emitted. So what's going to happen, right, is that the long wavelength, the short wavelength radiation, so this is short wavelength. So the short wavelength radiation is going to easily penetrate through the glass. It's going to heat up the black collector plate, right? And the black collector plate is going to emit long wavelength radiation. Now, guys, do you think long wavelength radiation has the energy to escape the glass plate?
No, sir.
No. Ashish, do you think the emitted heat rays from the black plate will be strong enough to pass through the glass plate?
Nah.
No, because we know that most of the heat is actually being absorbed by the black collector plate and the copper tubes. So only a little bit is being re-emitted. But the amount that's being re-emitted is not enough to pass through the glass plate. So eventually, you see inside here, all of this long wavelength radiation, it gets trapped and it builds up heat inside the glass plate because it can't escape. Do we understand that?
Yes, sir.
So this is the concept. Short wave radiation from the sun passes easily through the glass and is absorbed by the black surface. The black surface becomes warm, but because it is much cooler than the sun, it re-emits the energy as a long wave infrared radiation. Cooler objects always emit longer wavelengths of radiation. Long wave radiation cannot escape back through the glass, so it becomes trapped and the temperature inside increases. Do we understand the concept there?
Yes, sir.
Okay.
Yes, sir.
Right. So let me just add a couple notes, right? So easily passes through the glass plate, right? Also, it has high energy. Cannot escape. Low energy. Gets trapped. All right, so guys, do we understand the greenhouse effect?
Yes, sir.
Ashish, you feeling okay with it?
Yes, sir, that's easy.
Okay, good. And this is a bit more if you feels curious, right? But yeah, that's the basic concept. All right, so let's do this question here. All right, so Nikolai, give this question a read. Actually, no, Nikolai, just do the previous question. Ashish, give this a read for me.
The energy absorbed by the sun from the sun by a solar water heater is 360 kilojoules. 35% of the energy is transferred to 1.5 kilogram of water in the pipes. Calculate the final temperature of the water if its initial temperature is 30 degrees Celsius. Specific heat capacity of water is 4,200 joules kilogram, minus 1 degrees Celsius minus 1.
I remember when my students had a wrote this year and they saw this question, a lot of them was stumped. Let me see if you all are gonna get stumped. So first things first, how much energy is being absorbed from the sun by the solar water heater?
%35?
Wait, is actually 360 kilojoules, right?
Ah, okay.
No, because Nikolai, look at what they're saying. The energy absorbed from the sun by a solar water heater is 360 kilojoules. Seeing that?
Yes, sir.
So in other words, 360 kilojoules, right? But would all of that be absorbed by the copper tubes?
No.
No. How much is being absorbed by the copper tubes? How much is being transferred to the copper tubes?
35%.
Uh-huh. Ashish, you there?
Yes, sir.
Right. So if we know that the absorbed energy is 360,000 joules, right? And I know 35% is actually being transferred to 1.5 kg of water. What would be the amount of energy transferred?
65%. Oh, wait, what? Oh, 65% loss, sorry.
No, not 65%. They said 35% of the energy is transferred to the 1.5 kg of water in the pipes. So, do you understand that 35% is what is being transferred to the water?
Yeah.
So we need to figure out amount transferred to the water. That would just be equal to what? Talk to me, that would just be equal to what? How would I find that?
It will be 0.35 multiplied by 360,000.
Right, 0.35 multiplied by 360 by 10 to the power 3. Because kilo means 10 to the power 3.
Yeah.
So 0.35 multiplied by 360 multiplied by 10 to the power 3. And that would be equal to what?
126,000 joules.
Okay, so do you understand that that is the actual amount of energy that the water in the pipes receiving?
Yes, sir.
Right, so we know what the energy is, right? So E is equal to 126,000. Now they are telling us the initial temperature, right? What's the initial temperature?
The initial temperature is 30 degrees.
And they want us to figure out the,
So, a breakup.
and what do they want us to find?
So wait, so area lagin, I'm gonna join mag-meeting.
All right. Nikolai, in the meantime, what do they want us to calculate in this question?
The initial temperature.
Right, the initial temperature, right? No, not the initial temperature.
No, the final temperature, sir. Final, sorry.
Temperature, right? The final temperature. So is there any formula you could think of that has an initial temperature, a final temperature, energy, mass?
Yes, sir.
A formula comes to mind.
Energy, well, E equals MC delta T, sir.
Right, where delta theta is what?
T2 minus T1.
Right. What is the energy? What is it?
126,000.
Right, that's the energy being received by the water itself. So that's going to be 126,000. Hey, what? Let me just make. Hey, what? Right? Would you prefer to make T2 the subject of the formula now? Right?
Yes, sir.
Say that again.
Yes, sir.
Yeah. All right. So I would write this as E is equal to MC, right? T2 minus T1. Yeah.
Yes, sir.
What do I do next?
Here, divide everything
By what?
by MC T1.
No, you can't do that, eh? You can't do that. Why? Why? Well, the reason you can't do that is because T2 minus
Okay.
is in brackets and is being subtracted from each other. So you could only divide by MC. So if I divide both sides by MC, I end up with T2 minus T1 is equal to
E equals, well, E divided by MC.
right. And I want to find for
T2.
right. So how would I find for T2?
Well, we'll have to figure out what is E divided by MC.
You're not wrong, but I want to make T2 the subject of the formula. What do I have to do next? I want to make
Yeah.
T2 the subject.
You'll have to divide by the T1.
Now,
No,
T1
you
is
have to, you
from T2.
have to add it.
Yeah, I'll have to add T1 on both sides. Or it's and I'll move it across.
Yeah, I was going to say that, but then I realized you see we could do like add dividing or anything like that.
The only division we could do was this. Why? Because if you notice, MC was being multiplied by this entire thing. Anytime you have a product on top, you could actually divide.
Okay.
Feel that confusion, yeah? Yeah, exactly.
No,
If
not
I
really.
add 5x, right? And I could divide that by 5
Yes, sir.
because 5 is being multiplied by x, so I could divide by 5. Over here, MC is being multiplied by this entire thing, so I could divide by MC. You understand that?
Yes, sir.
All right. If I take that minus T1 and I move it across, that would turn to E all over MC. What?
Plus T1.
Right. What is E?
E is equal to 126,000 joules.
Right? What is the mass?
1.5 kilograms.
What is the specific heat capacity?
4,200.
Right, so I'm going to add T1 to that. What's T1?
30.
Right, so plug that into the calculator and let me know what you're getting for T2.
I get 50, sir.
Exact 50?
Yes, sir.
Good. Right, this question was a bit tricky in the sense of the algebra. The concept wasn't that hard. It was just the algebra was a little tricky. Right? So, talk to me, Nikolai. Why was the pipes made of copper?
Because, wait, what? Oh, because the copper is in contact with the black collector plate, which is a good absorber of energy, of thermal energy.
Hmm. A way to use some different words. A way to say conductor, right? So,
Okay.
so the pipes, right, are made of copper because it is an excellent conductor of heat energy. Excellent. All right, thermal conductor. Thermal conductor due to it having mobile electrons. Yeah, the part with the mobile electrons was a bit extra, right? And the main thing you need to say was the pipes are made of copper because it's an excellent thermal conductor, right, of heat. If you say thermal
Okay,
conductor,
sir.
you say conductor of heat. Thermal conductor means that it would conduct heat. So the pipes are made of copper because it is an excellent thermal conductor, right? Due to it having mobile electrons.
Yes, sir.
Right, so that's that.
Yes, sir. So wait, you can scroll up to the part one, please.
This one?
No. The one, go down. Yeah. Um,
Right, so take it in and let me know if you understand it.
all right. So explain from the formula E equals MC delta theta.
Sure, no problem. So in this question, they wanted us to find the what?
The final temperature.
Right. So you see, so in this question, right, the water was absorbing some heat from the sun, right? So if
Right.
water is absorbing heat, then its temperature is going to rise. So if we are talking about a rise in temperature or a change in temperature, the formula that should come to mind is E is equal to MC delta theta. Let me know if you
Right. Yeah.
and we know that oh, some fall down the massacre. Yeah, and we know that 126,000 joules of energy was absorbed by the water, right? That's how much heat energy the water absorbed.
Right.
So are you okay with the fact that I'm using E is equal to MC delta theta?
Yep.
Right. And isn't delta theta just T2 minus T1?
I didn't know that, but now I know.
All right, delta, because think about it, right? Delta theta is just change in temperature.
Right. Oh, uh-huh. Yeah. Okay, I understand now.
All right. Because delta theta, like I said, is just change in temperature. So the final temperature minus the initial
Same
temperature.
thing. Okay, right.
And to find for T2, I divided both sides by MC, right? So that will leave me with T2 minus T1.
So say E over MC. Okay.
If T2 minus T1 is equal to E over MC, then T2 would be equal to E over MC plus T1. And from there, you just plug in your values and you'll get your answer.
Okay, I understand. I just didn't understand the T2 minus T1. But now I know now.
All right, let me calculate that. Delta theta means change in temperature, which is equal to T2 minus T1. Final temp minus initial temp. Okay, yeah. So that's it for tonight. So guys, I'm not sure how tomorrow gonna run, but the next time I see you all, I want to look at gas laws. And after we do the gas laws, we are going to move on to waves and optics.
Alright.
Yeah.
Okay, sir.
Are they okay with thermophysics?
Yeah, this
Yes,
this
sir.
actually real light, you know.
Yeah, I like thermophysics. I like thermophysics. It's fun.
It's a nice mix between applying yourself and easy, you know.
Yeah, for sure. So the only thing we could go over in more detail is probably the thermometer part, right? But that's honestly just something I have to remember. Thermal expansion, you need to know the justification between that. So guys, if you apply heat to a substance or a material, the molecules on the inside are going to gain kinetic energy. So by heating it up, it's going to gain kinetic energy, right? And when you add kinetic energy to the molecules, they're going to vibrate faster. And now this would cause the molecules to move apart and increase their volume. And this is what you call thermal expansion, right? So yeah, how are we feeling about thermal physics? Okay.
Yes, sir.
All right. Well, good. Good to hear that. Is there anything you all want me to clarify before we finish?
No, yes, sir.
All right. So yeah, guys, see y'all later. When I see y'all later, right? I will see y'all later soon. Most likely those are doing maths. You see me tomorrow, right? You'll see me tomorrow.
What time, sir?
We will see. We will see. I will let you know. Probably be like 5 p.m.
Yeah, like nobody doing no specific people doing maths, sir.
Say that again.
They say like specific people doing maths.
Everybody is do maths. Like 4 to 5 p.m. around that.
Oh, okay.
Like the morning.
Oh, it's school bright and early in the morning.
Oh yeah, boy. Wait, I pack my bag and thing, you know. Pack my bag and thing. Yep.
Right.
Yeah. I pack my bag, I put my box lunch. I'm gonna say box lunch. I put the packed juice, you know. Yeah, boy.
So
Ready?
yeah, so yeah, I see the video of a man eat 6 box luncher.
Like joke.
Really, he is, you know.
No, that gone viral.
I said I joke, like I see more action in my school. Like I don't know if I know about Baji Pie, yeah, but anytime Baji Pie come, eh, I see a man in 10 boxes already. We feel to beat him up. Man
Wait.
take all Baji Pie for yourself, yes.
Yeah, that Baji Pie is coming real good. That's just real good, way. Wow.
And them teachers used to real hog that for themselves, boy. Gosh, man.
Sir, like they might get no food for the entire day or something, so.
I feel so. But they say Baji Pie, that tastes good, boy.
Wait, sir, what school you in?
I went Shiva Boys in the college. Yeah.
Good.
What school you from? It sound like you're from South. What do you mean in a bad way? I'm from South.
Nah, no, naps.
Oh, you go to NAPS. Okay. Uh,
Yeah,
and you're in Form 5, right?
no, 4.
Wait. Okay. Yes, I could have swear it was in Form 5. Could have swear it was in Form 5.
That
Nah.
was you know too?
Yeah,
See? Wait, nah, so Nicola, you in Form 5?
Of course. I write and see just now.
Alia real that time, way.
Yeah. That are lucky now. That was staying up all these hours.
Real.
yeah, boy. But yeah, guys, I will see. Like as soon as UE start back, chances are I probably wouldn't be able to do these lives. Most likely I'll just be focusing on my Form 4s and my Form 5s, right? And these lives might die down, unfortunately. But as soon as I get a chance, I'll do these lives. Nikolai, you go let your mom message me, right? Concerning the classes.
Yeah, she was supposed to call you Friday and then she was occupied due to work. So she
Mhm.
said she would have get the time she would have contacted you.
All right, well, no problem. Well, I'll see you next week, right? I'll see you next week in class.
Yes, sir.
Yeah. Later, guys. Have a good night.
Aye,
Yeah.
sir. I
Bye
see Tavon Ditch you already.
Watch him. I see him lie on anybody. Man,
Yeah,
Nah, devil.
sir, he ain't giving out the vibes, sir. You're supposed to be the vibes man, and he gone sleeping already.
Clip him. Sleeping, clip him.
next
Yeah,
thing,
he's staying up with you for the vibes, man.
hey boy. Hey boy. Man, leave me alone. Eh?
Yeah, you're running on fumes with them vibes now, boy.
Yeah,
Yeah.
boy.
Later, sir.
Yeah,
Thanks.
later, everybody.
Alright, sir.
It was nice meeting you guys. And
Yup.
it